Hey guys, welcome to IntelliPart. In today's world, artificial intelligence has revolutionized how we approach and solve problems. It is not only a skill that you need to have to get a highly paid job, but it's also to build something really cool. Artificial intelligence is an extensive, large field and it's very difficult to wrap your head around all the concepts that are involved in it. It's difficult to get past through the jargon and the terminologies associated with it. Keeping that in mind, we have come with this YouTube video on artificial intelligence. This video will teach you everything that you need to know in artificial intelligence as a beginner. Before we start, please do subscribe to IntelliPart's YouTube channel to not miss an update. Now, let me walk you through the agenda for today's video. First of all, we start to know what artificial intelligence is brief history and introduction. Then we move on to key major points in the history of artificial intelligence. Furthermore, we'll understand what an artificial intelligence algorithm is, whether it's supervised or unsupervised, and then we go on to the world of deep learning. Furthermore, we'll also like you to understand what is an artificial neural network, the topology of an artificial neural network, and perceptron, and many more. Then we take a closer look into one of the most popular tools used in your AI platform, your TensorFlow and your PyTorch. Going further ahead, we go into the details of your TensorFlow, learning concepts like tensor, computational graphics, feed-forward neural networks, multi-layer perceptron, and backpropagation. Last but not least, we make our own facial recognition program using computer vision and most of the popular tools in AI. Now, if you guys want to become a certified artificial intelligence professional, we recommend that you read through the description that's below. We at IntelliPart provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
One important aspect comes into picture when we talk about artificial intelligence. It is the year 1956, guys. Well, pretty much in the year 1956, the term artificial intelligence was actually coined. Well, how did this actually come to happen? I mean, I know a lot of us might actually know that it was coined at the Dartmouth conference and so much more, but what exactly is this conference? Well, in 1956, for a couple of years, basically, there used to happen, there used to be meetings and a couple of meetups where a lot of scientists and researchers used to come together under one roof. And this eventually was called the Dartmouth Conference. And here, basically, what started out as a summer research project, and it lasted about 8 weeks. And at the end of it, the product of their research and the product of basically their entire project was one person who coined out the name what is artificial intelligence, and it has ever been stuck with us right back from 1956, right? So I hope you got the Lord of the Rings reference there. So it's one conference to rule them all. It's basically one ring to rule them all if you haven't got that. And coming back to the presentation, so even after 64 years of the term being coined by Mr. John McCarthy, he is regarded as the father of artificial intelligence, guys. Even after 64 years, the world is still going mad, still going gaga about artificial intelligence when you think about it. Well, especially in the last 10 years, right? I mean, everyone is on the trend of artificial intelligence, and it's just gonna go like this for the next couple of decades is actually what analytics tell us, guys. So here's a quick excerpt that I read. Pretty much this is from the person called as Daphne Koller. She's a scientist at the Stanford Artificial Intelligence Lab, and she says that John McCarthy believed in artificial intelligence in terms of building an artifact that could actually replicate human level intelligence. Replicating a human is pretty much the toughest thing that even these big scientists could ever think of, and this was thought about way back in the 1950s as well. And she says that he was very happy with a lot of artificial intelligence today, because at the end of it is not replicating the human level intelligence that it was actually sought out to be. And it is said that he wanted artificial intelligence to pass something called as the Turing test. Well, if you guys know about the Turing test, just head to the comments section and talk to your fellow viewers and let them know about the Turing test. And if you cannot hold on to the curiosity, give me 2 or 3 more minutes. I'm going to tell you what the Turing test actually is, guys. So on that note, we need to check out what artificial intelligence actually is. So let me give you the breakup of the textbook definition, guys. Well, the definition goes like this. It's the theory and the development of computer systems, basically, which are able to perform tasks normally, which actually requires a human to do the task. It might be something as visual perception, speech recognition, decision making, and translation between multiple languages as well. Well, that definition will make sense if you actually go through it twice. I mean, this is the textbook term, right? So I usually keep all the sessions very simple for all the viewers from the beginners to the advanced level, guys. So you can have a lot of takeaway from it if we actually go about simplifying certain things for you. So the current goal of artificial intelligence, if I have to put it in one picture, is basically to tell you that it is just mathematics on steroids, guys. Because when you think about it, all artificial intelligence is trying to achieve is better ways and faster ways to do something that a human can do. A lot of terms like machine learning, deep learning, and come into the picture when we talk about mathematics as well. Because at the end of the day, to achieve artificial intelligence, we use so many concepts which involves a lot of mathematics and implementing this mathematics using code, guys. And at the end of the day, it's mathematics plus programming which will actually lead to us achieving cognition, guys. So what about the future? Well, again, achieving cognition has always been the goal, even of the even it's been the goal of the person who actually coined the term as well, and pretty much every one of his followers and everyone who wants to do something with artificial intelligence pretty much can tell you about how important and how amazing it would be to actually achieve cognition. Well, by cognition, I actually mean that getting a machine to replicate what a human can do exactly the way the human does, or even do it better as well, guys. So what do you guys think about it? What do you think in the future? What do you think artificial intelligence has a grip in the future? So head to the comment section and do let me know there. So then you might have heard of these terms, as I mentioned, right? Machine learning, deep learning, and so much more. Well, guys, I would love to explain all of these to you guys, but we've already put out a lot of videos on our YouTube channel, and we have amazing subject matter experts writing out blogs for us as well. So if you want to know more about these terms, machine learning, deep learning, or how they are used to achieve artificial intelligence in general, I suggest you head to our YouTube channel after this video, and then you can go about checking our blogs as well. But hey guys, make sure you stick till the end of the video, because I'll help you fast track your career to become an artificial intelligence engineer, and I'll be giving you a special coupon just for the viewers of this video, guys. So on that note, let us quickly check out the timeline of what artificial intelligence was, what it is now, guys.
Now, if you guys want to become a certified artificial intelligence professional, we recommend that you lead through the description that's below. We at IntelliPart provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
Let us head back to 1943. Well, it was the time of World War II, guys. It was almost ending, and pretty much this person is the reason, in my opinion, why World War II ended. I am a major history buff, and I believe personally, and many people agree with me, thousands of people agree with me when I say this, Mr. Alan Turing, who was a British mathematician, was the person who ended the world wars, because the Germans used a very nice coding system which was called as the Enigma, and they used to use that to send messages, and well, the Allied forces never got to know what these messages were because they were all encoded and they just look like rubbish. But Mr. Alan Turing developed the first artificial intelligence machine. He went about using a lot of mathematics, a lot of formulas. It took a lot of days, months, and years to go about cracking this amazing encoding system, which was basically generated by the Germans to go about sending their messages, guys. There's also a movie on that, so if you could watch that, it would be pretty nice as well. So this person, alongside breaking the Enigma, also it was called the Turing machine, basically, and then he invented something called as a Turing test. Well, what does the Turing test do? Well, I just told you 3 slides back that I'm going to explain it, right? So here it comes. So basically, consider this scenario that you are a human, and you obviously are humans, right? So basically, you're just sitting in front of your computer and you're asking a couple of questions to random people around you. And instead of saying it as random, let us consider 2 situations. One, your questions are being seen by a computer, and the other, your questions are seen by another human. So whenever you ask these questions, if you cannot figure out the difference between the answers that the computer can give and the human can give, I mean, if the answers are equally good where you cannot tell apart between the computer answer and the human answer, that particular computer which answered for you has passed the Turing test, guys. So that computer is intelligent enough to pretty much give you answers just like a human, and it can do a damn good job at it, guys. So this particular test, this sets the bar for, an intelligent machine, let's say, because if a computer can fool someone into thinking that they're actually talking to another person, then we can say to a certain extent that pretty much that computer has achieved enough cognition, because it is pretty much going about, let not say pretend, but it's trying really hard to replicate a human, and it's doing a good job at it as well, guys. So fast track to 1956, again the term was coined there, and scientists begin to tackle the concept. They were like, okay, now the term is set, let's work on it. And one of the top scientists, his name is Mr. Marvin Minsky. So basically his view, along with McCarthy's view, got him very good funding from the then American government, United States government, who basically hoped that, with the help of artificial intelligence, it will actually give them an upper hand in the Cold War, which was ongoing back then, guys. So pretty much Mr. Marvin Minsky along with McCarthy actually got good funding from the government, and they went about doing that as well, guys. So this another important thing happened in 1956 was Mr. Marvin went about starting the artificial intelligence laboratory at MIT, guys. And this lab, right from 1956 all the way till 2019 and 10 years from now, has been punching out amazing solutions to the world's problems, and it has been the most efficient laboratory in terms of artificial intelligence that the world has ever seen. And there are very intelligent people, and very much a force in these people which drive them towards achieving artificial intelligence, is what I can tell you, guys. And then again, a quick fast track to 1981. Well, 1981, artificial intelligence actually got commercialized. So this person called Mr. Ken Olsen, he's the founder of Digital Equipment Corporation, guys. So basically here he realized that, as a business leader, we can actually, start making use of artificial intelligence and start selling artificial intelligence to the common folk as well. And then fast track to 1997. This was one of the most important key moment, in my opinion, back in the 90s regarding artificial intelligence, because this was the first time there was a chess tournament conducted between the grandmaster Garry Kasparov. He was a world champion multiple times in chess. He actually played against IBM's Deep Blue. Deep Blue is basically their then supercomputer, and then Deep Blue actually defeated the world's best chess player at that point of time, guys. And people were saying that IBM's Deep Blue could actually think like God, because it was evaluating over 200 million moves in the game of chess at once. So for every move, it could bring up 200 million combinations of how you could go about playing. How amazing is this, guys? This is still 1997, and then artificial intelligence was already on the roll, and people could say it could think like God. I mean, that is a huge statement, and every time I go about reading about Kasparov or Deep Blue, I am amazed by the fact that this actually happened. In fact, multiple tournaments happened. You can probably read about it after the video, guys. And then fast track to the 21st century. We are finally at 2002, guys. I'm sure most of you might have heard of Roomba. Well, Roomba is a company, pretty much, it's from iRobot. It's basically a carpet cleaner, and it's a vacuum cleaner, guys. So it's a robot vacuum cleaner. So, in my opinion, again, this was another big achievement, because all it took was just few layers of behavior generating systems, which basically guided this machine around your house, around your living space, and it could efficiently clean carpets and floors autonomously without your help. And this has been sold across the world as well. There is 15 million units sold, and I use pretty much Roomba every day. So it basically has a docking station where it comes out of its docking station. It cleans our living room. It goes into the bedrooms. It cleans the bedrooms, and pretty much it just comes back, knows where its docking station is, and just goes back, charges, comes back again 2 times a day. You can program all of these, and it is an amazing thing, guys. It doesn't even, sometimes it starts doing it at the middle of the night, and I'm taken aback. Basically, you can set all of that. You can set the timings of which your robot actually starts cleaning and all of that. But it's actually amazing to know there is an autonomous system that I personally use to get my housekeeping stuff done, guys. So they've sold about 15 million units of these across the world, and that number is rising as well. And then coming to the maybe not so nice part of it, in a couple of people's opinion, but in my opinion, again, another amazing use of this is in war machines, guys. So many autonomous war robots were pretty much deployed to Iraq and Afghanistan. In fact, 2000 plus robots which are capable of war, everything from helping our soldiers carry heavy loads, defusing bombs which would be a threat to the life of the soldiers, patrolling enemy area, till all the way till they could make a stable war robot which is capable of inflicting heavy damage on the opposition forces, guys. Well, this is good in terms where our forces or any country's armies, navy or military forces are not put into immediate danger. Well, if the robot pretty much is shot dead or whatever, if it's malfunctioned or something, or if it's taken a lot of damage during the war, there is no human life lost there, and that is the important thing. That is the good thing. Well, the bad part of it is if this pretty much keeps on going, then every superpower, every nation who's a superpower will want to go about hoarding these. And then, I pray to God there isn't another big war coming. But if there is, then we will, see a lot of these war robots, guys. That's the sad part of it. And I'm sort of confident it really won't come to that. But if it does, then you can see a lot of robots there, guys. Let's just pray it doesn't come to that. Well, the next important thing in between the robots and the Tesla autopilot actually came about Google's self-driving car, guys. So I'm not sure if you guys know about Google's self-driving car, but instead of just telling you what the self-driving car is, I just thought of telling you the Tesla autopilot directly, guys. Here, basically, this was the biggest breakthrough in terms of artificial intelligence technologies, because Tesla, as a company in the United States, co-founded by Mr. Elon Musk, started providing cars to the public where the car could drive itself throughout. It could park itself, and all you had to do is basically sit in the car, and every 15 minutes or so you had to hold the steering to make sure that you're not sleeping or something. So how amazing this is this. There is a photo on your screen right now on the top right, if you can check it out. That is an actual photo from the car's dashboard, guys. So it basically instead of having a huge speedometer or something, it has this amazing display where it shows you, it detects all the cars around it, it detects rain, it detects the shortest distance, guys. You have to read about Tesla's autopilot, and I'm sure many of you guys will find it fancy, guys. In my personal opinion, if this is brought throughout the world, the capabilities of self-driving, that would be an amazing thing, guys. We've already seen a lot of companies actually bring out parking aids and autonomous parking, and it's basically called as parking help or whatever it is. A lot of companies like BMW, Skoda, and Mercedes, and all these big guys have already had autonomous parking capabilities. But when you think about when you think about how it goes about in every country, I'm sure it's very different. But then when you again contemplate about it, if this was brought to every country, it would be amazing, right? And then coming to 2019, guys, I mean, it's one more month to the end of 2019, and one amazing thing happened this year is pretty much in the field of medicine with respect to artificial intelligence, guys. Well, because artificial intelligence, as we all know it, has been helping the world in many different ways, and it has done so in the field of medicine as well. Well, it can be used to ameliorate reading time for digital breast tomosynthesis while maintaining or improving the accuracy of the reading. Well, what it's basically trying to tell us is that artificial intelligence is basically helping us to accurately make sure we detect cancer cells early on, guys. So this, again, we already know the victims of cancer, and we already know that it is an uncurable disease, and it takes a lot of time, endurance, patience, and so much more to go through with this, guys. But then if artificial intelligence can help us to check out what cells are harmful, what cells are harmless, basically what cells are benign, and so much more, then definitely this would help, right? Well, it has actually, the research has already been done. It is being implemented in many countries, and as a part of an artificial intelligence researcher, I am extremely proud of the fact that we've brought artificial intelligence down to the field of medicine, guys. So on that note, we need to check out what's next. We've seen all these different fields, and I'm sure there are hundreds of fields that I could have put in here due to the shortage of time, and pretty much to keep it to the scope of this tutorial for all of our viewers, I had to cut it down, guys. But take a second, head to the comment section, and let me know what you think about the views of artificial intelligences, and what are the other applications that you find amazing, guys.
Now, if you guys want to become a certified artificial intelligence professional, we recommend that you lead through the description that's below. We at Intellipaat provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
So, on that note, we need to quickly check out what are the types of artificial intelligence, guys. If we keep diving into the depth of these, then it might actually go out of the scope of this video. So, let me quickly tell you what are the types of artificial intelligence. Well, we have three different types of artificial intelligence, guys. One is narrow AI, next is general AI, and then super AI, guys. With narrow AI, it's basically, it is the concept which is meant to, assist or take over specific tasks and do it better than a human would do. Basically, an example of a narrow AI would be pretty much your mobile phone assistants, right? It can be Siri, Alexa, Cortana, and so much more. So you just make your work easier. Instead of opening the calendar app, setting your calendar, all you do is say, "Hey Siri, set my calendar for so and so." So that again is a very good example of narrow AI, guys. Coming to general AI, it's basically taking knowledge from one domain and transferring this exact knowledge into another domain. Well, general AI will almost require the intelligence of a human. If it will not require more intelligence, but you have to match the intelligence of the machine with a human or something very, I'm sorry about that, very close to that. Well, a good example to give you about this is, when you think about it, it's usually a very advanced level of chatbots. I mean, sure, Siri, Alexa, all these are amazing chatbots. And then general AI is again a lot of mathematics involved here as well. A very good example would be AlphaGo and so much more, guys. So AlphaGo is basically again another computer which beat the world champion at this game called Go. I wouldn't say it has the cognition level of a human, but pretty much, even though it sounds simple on the outside, it is actually very complex. And even the world champion said that this is the most intelligent Go player that I've ever met in my life. So that brings us to super AI, guys. Super AI is on another level, guys. This is I would say artificial intelligence, mathematics, programming, all on steroids at once. Because when you think about it, super AI consists of machines that are extremely smart compared to humans. They can outrun a human, outthink a human, outgun a human, and so much more. For either good or bad reasons, super AI is pretty much either in good terms or in bad terms, guys. I've never seen neutral sentiment about super AI, but for the scope of this video, all you need to know is that super AI is pretty much the domain which consists of machines that are extremely smart when you compare it to humans, guys. So on that note, we need to quickly talk about what is the cause for all of these intelligence, guys. So what makes artificial intelligence intelligent? Well, in my personal opinion, the art of training a machine is amazing, guys. When you think about it, you can go about showing your computer images of cats and dogs and asking it to classify it for you. I mean, from our childhood, we have been trained by either school or by family members or friends to know what a cat looks like and what a dog looks like, but your computer does not. It might have taken you 3 years to figure out the differences, or 1 year to, let's say 1 year, you took 1 year to figure out the differences. Your computer will probably take 5 seconds or 10 seconds to figure out this entire thing what took you 1 year, guys. So when you think about it, everything from a very simple cat dog classifier all the way till achieving cognition, in my personal opinion, is just art, guys. Because at the end of the day, taking a concept which does not exist and bringing it right up to the level of a human being, and in a lot of people's personal opinion, human beings are the most intelligent species out there right now. Well, unless there are aliens and all the conspiracy theories. Well, jokes apart. Well, coming back, bringing a machine up to the level of a human is definitely achieving cognition, and it's being done right, guys. So we need to think about the challenges we face when we go about making artificial intelligence intelligent, guys. There are 4 important points which pose as challenges. One is knowledge, guys. Because again, when you think about it, when you have to train a machine to figure out stuff on its own and hold these and implement it later is very difficult. This brings us to the second point. Well, if you think getting your machine to hold information and to make sense of it is difficult, then think about learning, because you can learn at a rapid pace, at a slow pace, or whatever it is. But getting your machine to learn, getting your machine to understand about a new concept, contemplate about it, work with it, analyze it, store it, and use it later is something very difficult. And this brings us to the next thing, which is problem solving. Even though you got your machine to have all the knowledge and learn very easily, it needs to go about implementing all of these in a perfect way, guys. Well, it can have the knowledge of all the worldly things which goes by, but what is the use if it cannot solve a problem? Because again, all the artificial intelligence terms or whatever points towards artificial intelligence mostly is a problem, right? Anything in the field of military, medicine, or so much more, we give the developers, the researchers, the scientists a problem so that they can solve it for us easily using artificial intelligence, right? So if your machine cannot solve a problem, then it is pretty much no good, guys. And this is actually very tough to achieve as well. And next comes obviously cognition, as I've been telling you for so many times right now, because again, bringing your machine up to the human level is again a very daunting task, guys. And in the middle of this, let me give you a very quick fun fact. I'm sure most of you guys might have heard of it already. Artificial intelligence has been used in terms of litigation, litigation and law and court and so much more as well. How? Well, I'm sure you guys have heard of JP Morgan, right? They are the banking giants of the world, and they came up with an artificial intelligence model which basically was used to go through and analyze some legal documents. You wouldn't believe the numbers, and the first time I read this a couple of months ago, I was taken aback, guys, because when you think about it, it reduced the workload from 360,000 man hours to a matter of seconds. Think about it, 360,000 hours of job. This is what it takes a human to do it. But as soon as they implemented that model, it just took the model a couple of seconds to do it. And I have read that the model is very accurate as well. So when you think about it, think about the odds, 360,000 hours and a couple of seconds. So, if you didn't know this fact, then I hope you find this very entertaining, and I hope you guys feel very interested about this fact at the same time, because we already know artificial intelligence is being used in every field, but not many of us know how it was actually used in litigation, right? So I just found it very interesting to tell you guys about that. And this brings us to the dark side of artificial intelligence. Well, is there a dark side? Well, you remember Elon Musk, right? The founder of Tesla, the founder of SpaceX, the founder of SolarCity, and so much more. He's basically a billionaire entrepreneur, guys. Well, he says that, at least when there's an evil dictator, that human is going to die. But for an artificial intelligence being, there will be no death. It will live forever. And you will have an immortal dictator from which, you can never escape. So, I am sure our views on this particular topic, we can debate about it all day, all night, and we're going to have very different opinions about this. And we need to respect people with very different opinions about this, because at the end of the day, all of these, what we look at as different opinions actually come under one umbrella, and it helps develop artificial intelligence in the right way, guys. So, I hope there is a good... I am in fact, I am sure that there is a good way and a good path for the development of artificial intelligence, but you can never know at any point of time. Well, according to a lot of experts, that it might take a turn for the bad as well. Again, let's hope that it doesn't go there. And on that note, we'll quickly bust a couple of myths and facts, guys. So the myth is that superintelligence by the year 2100 will be inevitable. Well, when you think about it, it might happen right now, it might happen in a decade, in a couple of years from now, or it might never happen at all. To achieve superintelligence, again, as we've been talking, is a very, very, very challenging task, guys. And the myth is that, only people who do not know about Luddites are basically people who are not very well informed. That only these people are worried about artificial intelligence and all of its bad things for the future. Well, not exactly, because even many top artificial intelligence researchers are concerned about how it's going to go about in a good way or in a bad way as well, guys. Another myth is that artificial intelligence is turning evil, it is turning conscious, and so much more. Well, the actual worry that we need to go about doing is, artificial intelligence actually turning to be very competent with a goal that would be misaligned with our particular goal. So it might take a very staunch deviation from what we set it out to be, and it could do something on its own. So that is the actual worry when you compare to the myth. And then to bust another couple of myths, people say that robots are being the main concern, like those Terminator movies and whatnot. Well, again, here as well, misaligned intelligence is again the main concern, because we live in a world of technology. In every device, every home, I'm sure most of the world is connected through an internet connection, right? So you will not need an actual robot in case if something goes wrong as well. So that is something to think about. And then artificial intelligence cannot control humans is a myth. Well, intelligence actually enables control. So, we do this very sad thing where we trap animals in cages and create zoos around them. I mean, I'm not much of a zoo fan. I hope I do not offend anyone regarding that. So we are smarter than tigers and all of these other animals, so we can go about controlling them because we are smarter. Now think about a machine which is smarter than humans, it can go about controlling us as well, right? So that is a fact to think about again. So machine cannot have goals. Well, this is wrong, because again, let us say two planes are fighting in the air. It's called as a dog fight. So two planes are fighting, and the plane behind just launched a missile. If you have seen in a lot of movies that I'm sure you would have, this missile exactly knows where the plane is and to go hit it. This basically works on the concept of heat seeking. Well, it has detectors in the front of the missile which will find the hottest thing it can see and then just go hit it. So the hottest thing in a plane is in the plane which is in front is its engines. So this will basically chase the plane's engines and hit the engines. So that is a heat seeking missile for you. And then the next mythical worry is that super intelligence is just years away. Well, not really. It is a couple of decades away, as I've pretty much told you. But again, it might take way longer than 2 decades, 3 decades, 4 decades, and so much more to, just to make it safe for us to use as well, guys. So that is all with the dark side concepts that I had to just inform you guys in case you weren't knowing. So this brings us to the next concept, which is basically the domains in which artificial intelligence has its hold, guys. Again, number one, as I've been saying for a long time, is healthcare, guys. That is the best thing that I've seen artificial intelligence being put to, and there are so many things live as well. So it has been so subtly integrated into your lives that you would not even know it is there. When you think about it, probably you just open a health app installed on your mobile phones or your computers. You'll be talking to a chatbot instead of a human, and you wouldn't know it. Most of the time you can just set an appointment with your doctor and ask more information about your appointments and so much more by just talking to a machine instead of talking to a human on the other side, guys. And from that till helping detection and curing of cancer is again an amazing thing in my opinion. And the second thing is stock trading, guys. As an investor personally, I could sort of relate on this as well, because if stock trading again is a very tipsy-turvy world, right? So sometimes you lose money, sometimes you make a lot of money. But if you had a way, if you had a different approach, if you had a more intelligent being to look at graphs, to look at data, and to make better sense of it than an expert trader, then that would be an amazing thing, because you could end up making more money and losing less money at the same time, right? So this brings us to another next thing, is sales, guys. Well, this is a personal recommendation from me, because here at IntelliPath, let me tell you how we implement machine learning and artificial intelligence for our sales team, guys. So we get about 10,000 or 15,000 sales leads every single day. Imagine calling those 10-15,000 people, guys. So it would be a daunting task to go about doing it, but we have a machine learning model which is in place, which basically helps filter out these people, categorize them, and make sure it basically makes sure that they get in touch with our course advisors, and then later our course advisors basically help them get the course that they were actually looking for, guys. So this makes the entire process of going through the part of sales a very interesting, a very simple, and we get lot of analytics from that as well, guys. So this is us at IntelliPath using artificial intelligence to help out you learners as well, guys. So that brings us to my final thoughts regarding artificial intelligence. So you might have this question at this point of time: will artificial intelligence take over the world? Well, when you think about it, since you are the most intelligent, since we are the most intelligent being right now, it is as good as we are, because if we are extremely good at programming, our artificial intelligence model will be extremely good as programming. So it totally depends on us and how good we are. Unless machines start writing code and they can write it better than us, right? So until we go there, we are the most intelligent beings we know, and then artificial intelligence will be as good as we are, guys.
So now let's actually get a bit deeper and understand what is intelligence. So intelligence can be defined as one's capacity for understanding, one's capacity for self-awareness, one's capacity for learning, and one's capacity for problem solving. That is, how well is something or someone able to understand? How well is someone able to learn new things? And how well is someone able to solve problems by themselves? So, now that we know what is intelligence, let's understand what is artificial intelligence. So, when you apply the same intelligence to machines, this is known as artificial intelligence. Now just imagine there's a machine which can understand things which are normally understood by human. There is a machine which is self-aware, and there is a machine which can solve problems by itself. Now that's just amazing, isn't it? Right. So this is the artificial intelligence which I'm talking about. So now that we also know what is intelligence, I'll ask another question. So tell me, what is it that makes humans intelligent? Well, we as humans can reason, we as humans can learn, we can perceive, we can solve problems, and we also have linguistic intelligence. That is, we can figure out what is someone else saying, and we can also understand the grammatical intricacies of different languages. So again, my question would be, what if a machine could exhibit all of these factors normally shown by a human? Again, that's just amazing, isn't it? So this is what is known as artificial intelligence. So a machine which can show traits normally shown by a human, that is known as artificial intelligence. Alright, so now that we're clear with artificial intelligence, let's segregate AI, ML and DL. So normally most people get confused between artificial intelligence, machine learning and deep learning. So this is where I'm going to help you out in understanding the difference between these three. So we have AI at the top, and you can consider machine learning and deep learning to be subsets of AI. So again, machine learning and deep learning are just ways to achieve artificial intelligence. So I'll restate it again. Machine learning and deep learning are just ways to achieve artificial intelligence. Now, machine learning is that part of artificial intelligence which aims to teach the computers the ability to do tasks with data without any explicit programming, right? So we don't need to do any explicit programming, and the algorithms do tasks by themselves. And in ML, we mostly use numerical and statistical approaches to achieve artificial intelligence. And then we have deep learning, which is actually a subset of machine learning. So first we have AI, and then we have ML, and then we have DL. So deep learning comes in where machine learning fails, and we apply deep learning through something known as artificial neural networks, about which we'll obviously learn later. Right. So now let's understand artificial intelligence in a bigger set. So as I've already told you, artificial intelligence is the superset under which comes machine learning, under which comes deep learning. And then machine learning and deep learning are basically ways to achieve artificial intelligence. Now these are the different areas of research of artificial intelligence. So you have ML, again a part of ML is deep learning. Then we have natural language processing. So over here we basically understand what is spoken or written by a human. And then we have speech, where we either translate the speech to text or we translate the text to speech. The next subfield is robotics, and then we have autonomous vehicles under robotics. So Google's self-driving car is an example of this over here. So now that we've also understood the difference between artificial intelligence, machine learning and deep learning, let's see different examples of machine learning around us. So most of you would have shopped on Amazon. Now, when you go into Amazon, you see that there are some products recommended to you. Now, how do you think that would happen? So this is something known as recommendation engine. And recommendation engine is nothing but a component of machine learning. So let's say you and your friend buy similar products. So your friend buys 5 products and you buy 3 products. Now, out of those, whatever 3 products you buy are same as what your friend buys. So let's say the common products are an iPhone, a back cover for the iPhone, and a Bluetooth headset. Now let's say the other 2 products bought by your friend would be a MacBook and a mouse. Now since there are 3 products which are same between you two, this is why the products which your friend has also bought, those are the products which will be recommended to you. So, on the basis of the commonality between you and your friend, you will be recommended a MacBook and a mouse as well. So, this is nothing but a concept of machine learning. And then we have Amazon Alexa. Amazon Alexa is a really good example of speech recognition. When you say Alexa, turn on the lights, it'll turn on the lights. When you say Alexa, book a ride for me, it'll do exactly that. When you say Alexa, order a cheese pizza, and that is exactly what Amazon Alexa will do. Now, Alexa is just a machine, right? But when you say do something, order a pizza, book a cab for me, turn on the lights, how is the machine able to understand all of this? So, the idea behind this is speech recognition, and that is again a component of machine learning. And then we have Netflix's movie recommendation. So, let's say you watch two TV series. First TV series is Friends, and the next TV series is Big Bang Theory. And since you watch these two TV series which belong to the genre comedy, that is why maybe you will be recommended How I Met Your Mother, or you can be recommended Silicon Valley, or some other TV series belonging to the comedy genre. So this again is machine learning. And then we also have Google traffic prediction. Let's just say you're traveling in your car and there is huge traffic there. You desperately want to get out of the traffic. So you turn on Google Maps, and Google Maps tells you the best direction from where the traffic would be the least. Now, how does Google Maps do this? This again is machine learning. So now that we've looked at different real world applications of machine learning, let's actually understand what exactly is machine learning. So, as I've already told you, machine learning is a subset of artificial intelligence which gives the machine ability to learn without being explicitly programmed. So over here, data is the key, or in other words, you basically teach a machine how to learn without any explicit programming, and the machine learns with the help of data. So now that we know what exactly is machine learning, let's also understand how does machine learning work. So as I've already told you, machine learning depends totally on data. So first, we take in a data set and divide it into two parts. So the first part would be the training set, and the second part would be the testing set. And we will train the model on top of the training set. So now, once we train the model, we will give it new data and check for its accuracy on top of that new data. And if the accuracy of that new data comes out to be good enough, then we will go ahead and use that machine learning model. On the other hand, the model which you built, if the accuracy of that model is not good enough, then we'll go ahead and fine tune that model till we get the desired accuracy. This is the basic premise behind machine learning. Now let's look at the subcategories of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you can consider that the learning is guided by a teacher. So we have a data set which actually acts as a teacher, and its role is to train the model or the machine. So once the model gets trained, it can start making a prediction or decision when new data is given to it. So let's take this example. So over here, we are training this machine by giving it samples of data. So over here, the data is nothing but different images of apple, and along with each image of apple, we are also giving it the label of the image, right? So this image goes with its label, which is apple. Again, this image goes with its label, which is apple. Again, the same with these two, right? So we are teaching this machine that whenever it sees an image something like this, it is nothing but an apple. And after time, when we give it a new data from whatever learning it has done, it will predict whether it's an apple or not. So on the basis of its learning, this machine predicts that there is a good possibility, there is actually 97% possibility that the image which has been fed to the machine is nothing but an apple. So a use case of supervised learning could be spam classifier. So spam classifier basically means that whether the email which we get it's a spam or not. And that is done on the basis of different textual parameters. So let's say a genuine email wouldn't contain too many exclamation marks. It wouldn't contain a catchy headline and so on. But on the other hand, if it's a spam email, maybe it'll contain a lot of exclamation marks with maybe a lot of numbers, and it'll have statements like, hey, congrats, you've won a lottery, or hey, could you help me out? So this spam classification is basically an example of supervised learning. Then we have unsupervised learning. So in unsupervised learning, the model learns through observation and finds structures in the data. So once the model is given a data set, it automatically finds patterns and relationships in the data set by creating clusters in it. So what it cannot do is add labels to the cluster. Like it cannot say this is a group of apples or mangoes, but it will separate all the apples from mangoes. So over here we have this set of images. Now this unsupervised learning model which is applied on this, it will segregate these fruits on the basis of similar characteristics. So over here we have segregated these 4 into one cluster, these 3 into second cluster, and these 3 into the third cluster. Now even though the unsupervised learning does not have any labels, it has still segregated these 3 into 3 clusters, right? So the machine over here does not know that these are apples or these are oranges or these are bananas. Yet it has segregated these 3 on the basis of similarity of characteristics. So it found out that these 4 objects are similar to each other, and there is quite a bit of variability when it comes to these 4 objects and these 3 objects. Similarly, this machine was able to figure out that these 3 objects, they are quite similar to each other. But when compared with these 3 objects, they are very dissimilar. So this is the underlying concept of unsupervised learning. And a good example of unsupervised learning would be again Netflix movie recommendation. So over here, the movies are segregated on the basis of different genres. So over here, TV series like Friends, How I Met Your Mother, and Silicon Valley are clustered into one group because those come into the same category. Similarly, movies such as Secret Superstar and Dangal could come under the same category because they have the same lead actors. So over here, we are segregating the movies on the basis of similar characteristics, even though there are no labels in it. And it's finally time for the third machine learning type, which is reinforcement learning. So over here, there is an agent and there is an environment, and the agent interacts with the environment and finds out what is the best outcome for it. So it basically follows the concept of hit and trial method. The agent is rewarded or penalized with a point for a correct or a wrong answer. And on the basis of positive reward points gained, the model trains itself. So let's take this example. So over here, this self-driving car would be our agent and the road is the environment. And this car is interacting with this environment. So it will observe the environment and it has two choices over here. So either to go straight or turn right. Now, let's say this agent or this self-driving car decides to go straight. Then what happens is it goes and bangs straight into this barricade. So then it realizes that the action taken by it was not in its best interest, and that is why it is penalized. So since it is penalized, it realizes that the action taken by it was wrong, and that is why from the next time onwards, it will do the opposite action. So instead of going straight, it will take the right turn. And when it takes the right turn, it realizes that the road is correct and the agent is rewarded. So this is how reinforcement learning basically works. So the agent interacts with the environment, it takes an action, and if the action turns out to be incorrect, it is penalized. And if the action turns out to be correct, it is rewarded. So this cycle goes on and on till it completely learns its environment properly. And the best use case of reinforcement learning is again self-driving car. So companies such as Tesla and Google are working on these self-driving cars. So just to sum it off, these are the three different types of machine learning algorithms. So we have supervised, unsupervised, and reinforcement machine learning. So under supervised, we have regression and classification, and in unsupervised, we have clustering techniques, association analysis, and hidden Markov model. And then the third is obviously reinforcement learning, which works on trial and error method. And if you want to do some really cool machine learning projects, you can check the sites out. Now let's look at some limitations of machine learning. So when it comes to machine learning algorithms, they would require massive stores of training data. So again, as I've told you, machine learning is totally based on the data which it has. So if you have more amount of data, only then it will be able to give correct accuracy. So let's say you take in very small amount of data, and there's a good possibility that the results which you're getting are very biased or very incorrect. And also, error diagnosis is quite difficult when it comes to machine learning, because again the amount of data is very huge, and wherever there's a mistake, you'd have to go through the entire algorithm which you've written and then find out that particular mistake by yourself, which is very difficult. And also when it comes to machine learning algorithms, they're not really that creative. So these ML algorithms are built only for one specific purpose. So let's say I'll build a machine learning model which will predict whether it will rain or not today. Now, if I want to use the same model to predict the stock prices, that will not work, right? So basically one model is built only for one particular task. So this is the lack of creativity that I'm talking about when it comes to machine learning. And also there are a lot of time constraints as the model has to learn through a lot of historical data. So that was everything about machine learning. Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task-specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations. And these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's say if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it'll automatically learn all those features of the data by itself, and it'll be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also, another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language, and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer, and this input layer automatically extracts the features by itself. Now that data is sent to this hidden layer which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So, dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat, and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these three main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals and the cell body processes these signals. And the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bias that are randomly selected. So here we have W1, W2, W3 going on till Wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have three arrows which correspond to the three inputs coming into the network. Now for these three inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the three inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to this sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have two inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have two different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these two classes. So is that really possible? Can we draw a linear line which can segregate these two classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is, when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between -1 and 1. So one advantage of tan h function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here, after the first iteration, error value is 2, since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function, which would give us a non-linear output. So this process until here is known as feed forwarding. Now, if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So today we'll cover just that. So let's start with TensorFlow. So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is, model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4j. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4j is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4j is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages, such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this, I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly, I'll also create a floating type constant and I'll store this in con2. So I'll type TF dot constant and the floating value would be 3.14. Now after this, I'll create a string type constant. So again, this would be TF dot constant, and the string which I'd be giving would be this is Spara. And finally, we have a Boolean type constant, and I'll store this in con4. So this will be TF dot constant, and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type Boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type sys equals tf dot session, and I'll hit run. Now I will run all of these inside this session. So I will type ses dot run, and let me go ahead and run all of these: con1, con2, con3, and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol, and then I'll take in the next constant, and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol, and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type ses dot run, and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant, and inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4, and 5, and I will add this list with the next constant. And this time, the second constant has the values of 5, 4, 3, 2, and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant, and this will have values, let's say the same values, 1, 2, 3, 4, and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2, and 1. Now I'll hit run. Again, I need to run these two inside a session. So ses dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is our result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant and the value of this constant would be TensorFlow. Right. Now I will run this and let me execute this inside a session. So ses.run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow. Right, so that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax, and inside that we just give the data type of the variable which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A and tf dot placeholder, and this would be of integer type. So tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So ses dot run, and I want to see the result of b. So I'll put in b over here. Now, since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right. So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now, similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4, and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8, and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name. And let's say the value of the string is I am. Alright. Now let me run this and I'll execute this inside a session. Ses dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, So let me create this placeholder. I'll name this as str name. And since there's a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string, which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys.run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1. And we can create a variable like this, tf.variable. So guys, you need to keep in mind that this V over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20. And this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So sys.run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable, sys.run var1. Right. So we have the result of var1, which is 20. Now, since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1, and the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update, and the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run. Right now, let me run this inside a session. Sys.run, and I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. W x plus b, where w and b would be variables and x would be a placeholder. Right. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf dot variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf dot int 32. Now similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf dot placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf dot int 32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals tf dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this, and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So let's go back in 1980s. There was this crazy guy called Geoffrey Hilton. He proposed that we could mimic somehow the mind, how a human mind works, and we can mimic the way it works, so that we can also try to make a thing out of it, so that whatever our mind is doing artificially, we can also do that thing. So he proposed a paper, and everybody said that, Hilton, listen, you are doing something wrong. This is not what is right. And everybody, didn't like uh, the way things were going on. But after 20 years, almost in late 90s, around 1999, he again came up with this paper. He brought in his paper, but this time with a proof, and he won a contest that is called ImageNet in 2004. This time he came back and everybody had to listen. So we were at 2004 when he won the ImageNet. I have two people who I've already told that ImageNet is ImageNet is actually in a competition. It is held by a joint vision of Stanford plus Princeton University. These guys come up and they downloaded a corpus of images. Now they have a very large collection of images, around 1 million images, around covering 1,000 categories. They have. You can just click on explore and you can see this tree around here. So what you have to do is that you have to make a model out of it, so that you can classify the images. So people used to make hand coded classifiers, and they were working, but at some stage they had to fail, because now let's say that fish, you are trying to detect a fish, but fish cannot every be in the same manner in which you are building the hard-coded thing, right? Or let's say that you are trying to detect a cat, and then you say, okay, top right if it is a eye, top left it is a eye, and then it's a squishing mouth, then it's a cat, right? But now the cat face will not always be available to you in that particular fashion, right? It might be a top view, a side view, a bottom view, any view might come up, and at that time people used to fail. But in 2014, 2004, when Geoffrey Hilton came with his paper, the competition he won was with 94% accuracy, and that was never achieved, and it surpassed the human accuracy also. So that was where, when people started listening to him and he came out, then he proposed slowly that, okay, that this is what I think, that artificial neural network is nothing, but that we are trying to mimic what is happening in our own mind, right? So if I say that what is the theory, what Joffrey said about neural network is that he said that an artificial neural network is a computational model that is inspired by the way biological neural networks in our brain human information possesses, right? So I mean, most of you know this thing, that that our nervous system is made up of axons and okay, I'll show you the photo, that it is made up of axons and brains. I show you the photo and you might be able to. See, this is actually how a human nervous system is. Most basic diagram, and everybody of you might have seen this. So how this works is that there is a exact replicate copy of this. If I copy this, and you can attach it back here again. So these are the axon terminals that are connected to dendrites again, and this is how it flows. So let's imagine that your fingertips where you can have your dendrites, and these are like small particles again of your pure neuron connected to your brain. So this is how there are like millions of these connected, and they're connected. If I take this, okay, one more feature of Jupyter Notebook that you already know, that you can add a markdown language. So what I do is I do escape M, and then I'll write HTML inside it. So I write img src is equal to, right? This is how you can write your, in this you can add that this is, right? Let's now look at it one by one, slowly. Okay, so these are called dendrites. These dendrites are the one who are like septicles. These are the one who are responsible for catching all the information and sending it forward to the nucleus. Now nucleus processes this thing and it sends to this axons and again throws it out to the axon terminals. Now imagine again that this is this copy, this is again replicated here, back here. So you can imagine that these dendrites are connected to these axons, right? And then they're flowing. Now imagine, let's say that you touched a very small, a very hot glass, right? The moment you touch the hot glass, the dendrites at your fingertips, they sense that something is very hot there. So they send this information to your brain, okay, that this is hot. Now imagine this dendrite is processing the information, sending it to terminal to dendrite, and dendrite to terminal. It goes on until it goes to your brain. Now the brain says that this is very hot. You should remove your hand. Okay. Now this process is again flowing back to the dendrite, the original dendrite here. Let's say that this is the original dendrite here. Okay, and your brain will say that this is really hot. You should remove the fingertips from the glass. And now when I'm saying that this information is going on, believe me, from your fingertip to your brain, there are like millions of these dendrites who are connecting and flowing this information. Now again, a process of reversal information flow is going on, and this time your brain is sending a signal that remove your hand from the glass, and this is again going back to the fingertip, and then you release your hand from the glass. But in real life, when you touch the glass and when you remove it, how much time do you take to remove this? It's just some nanoseconds, right? I mean, less than. Your reflexes are very strong. You just remove the hand out. But imagine what is happening when you do this. Your brain is not, your hand is not taking the decision of removing that. You might think that, okay, my hand is taking the decision to remove that. No. The hand is like a slave of brain. So every body part of ours is like a slave of a brain, right? Whatever we are doing, it is sent by the brain. The information is sent by the brain, and then it's doing. This is how your body works, right? So it's a slave of your brain, and the brain sends the information, remove or attack, whatever it is, then it reacts. But it's really fast, right? Similarly to this way only, Joffrey said that, okay, this neural network, this is how even I will also build a neural network. Now I'll show you how a basic neuron looks like. Here it is. This is the image. You write it. Basic neural. It's not a network, it's just a neuron. But this is an artificial neuron. So Joffrey said that, okay, this is how I propose. Let's do the following. Let's say that your hand is not doing anything. Your dendrites or your nervous system is not, this basic neuron is not doing anything. Imagine that it's doing nothing. But it is reciprocating the information. But how it is reciprocating the information? By activating itself. So when you touch a hot glass or something, it activates itself, and then only it's transmitting the thing, right? Now imagine if this would have not activated, it would have sent nothing, right? So this is also playing a very crucial role. See, brain is sitting somewhere like a million neurons far, right? He doesn't know what is happening to your hand until and unless this neuron is sending the information. So what information will the brain process if it doesn't have the information? So these guys are very much responsible for sending the information, and they send the information only when they're activated. So this dendroid will become, this nucleus will become activated, then only it will send the further information. And see, there is also a basic kind of a information processing is going on. It doesn't mean that these dendrites are just sending blank signals. See, I'll tell you more depth inside. See, these dendrites, they collect the information. These dendrites, they collect the information and they send it to the nucleus. Now, nucleus thinks that should I process this and send it forward? Yes or no, depending on that, nucleus send it further. Right. Now, how is nucleus sending is? Nucleus has a particular threshold value. After processing it, it says, okay, if I am activated by that processed value, it will send it further. If not, it will keep it to itself. So this is also how a basic artificial neuron, when I say artificial, it means that the one that we are building right now in deep learning, right? This is also built. Now what is happening is that imagine this round thing that you're seeing is the nucleus. This thing is a nucleus. But this is a nucleus, right? And these are the dendrites to it. This one, this X1 and X2. This is the way of thinking how we are intimating, and this is the tail, axon tail, and it is again connected to again a neural network. So it's a chain of multiple neurons going on. Now, if we go mathematically, what is happening inside this? It is nothing but a linear combination of all the inputs with a bias. I just like went to the very human biological way and I just sent a sentence. It's doing nothing. What it's doing is that it collects the input. Let's say that you have two inputs. Let's say that you have two inputs, x1 and x2. These are your two inputs. Now to every input, you will give some weightage to it. Let's say our weightage is here. This weightage is called W1 for x1 and W2 for x2. Correct? Now what I said, it is trying to build a linear regression, right? So what it does, it multiplies the weight of the corresponding input to itself. So W1 x1 plus W2 x2 plus it adds a bias to it. Now you will ask what is a bias? I'll say imagine that there is another input called x0. There is another input called x0 and the value of x0 is equal to 1. The value of x naught is equal to 1, and there is this weight associated to it that is called w naught, right? So this bias is added to it, and then you add this. That's it. You plus all these values, multiply plus all these values, and you give this output to something called y. This is all a neuron does. Make sense? Any questions? Please ask. It's very important that you build the intuition that what is happening here. So this is the most basic. It's the smallest part of a neural network that you can pick. And the smallest part of a neural network is doing this. Like it takes all the inputs that are coming to itself, give them some weightage, multiply the weightage to the corresponding input, and then sum all these, and then add a small bias to it also. That's it. Over. How is this weightage and bias being introduced? That who is okay, x1 and x0, x2 and x1, I can say okay, someone is giving to us the input that what is the temperature of the glass. Let's say it is coming from the outside environment. X1 and x2 is coming outside, but who is giving this w1 and w2? So okay, so the answer is that in a artificial neural network environment, at the very first instance, they are randomly allocated to it. So see, you all guys have learned ML, right? So how does ML work? ML says that I know the output, and depending on the output, I have to give some weightage to these inputs so that they can give me the output. Now you know that the output will be y. You know that the output is going to be y, right? Now you want to make some equation where y is equal to x1 plus x2. Okay, and now this is not the correct answer, right? X1 and x2 will never give you y1. So what you do, you add some w1 here, some random w1, and then here random w2. What it will do, it will not give you the answer. W1 and W2 will not give you the answer. You will do some corrections again in W1, W2, and ultimately it will give you Y. So this is what is happening. At the very first instance, you will take W1 and W2 as random. First is that does the process is reverse? Yes, it also reverses itself. The model will not only go from x1 x2 to y, but it can also come back from y to x1 x2. And second, let's say that he's asking Shivam, does it process recursively? Recursively, just imagine that there are like thousands of, now I'll draw it again to show you. This is just a very basic one, right? Now imagine what is going on here is that this is the small that you saw, right? X1, X2, and it is giving some Y. Now here it is again, there is a X1, X2, and then this is giving me Y. Now this Y and Y1 will become an input for some other cell. And then it is giving here. So are you imagining how will it look like? This becomes this, and this will become again an input for some other. So these are like connected. These are like throwing information from one to another, one to another, one to another, right? But this is how it works. This is how a small network looks like. And this is if I write down the theory, it says that the basic unit of computation in a neural network is a neuron, or often called as a node, right? And came write it very right. This is called a node, or you can say it a unit also. So it receives input from some other node, from an external sources or external source, that I was saying right also, right? The x1 and x2 might be an input from another neuron, or it might be given to you directly from the external environment, right? Computes the object. Each input has an associated weight to it, which is assigned on the basis of its relative importance to other. The node applies a function f to the weighted sum of this input, right?
So we'll be having the students' data. So whatever the marks, based upon their marks, so we have to decide the grade. So we have to adjust whether the student is passed out or failed. So we will be adjusting the marks based upon the grade.
This is a very hard-coded problem, I think. But let me take an example that you're working on a machine learning problem where you are trying to find out the loan defaults, right? That in bank you have multiple people who take the loan. Now the bank wants to know how will this person repay the loan or not, right? Now you already have a historical data with you. The bank will give the data to you. Okay, let's say that this is the data with you. So in that data, you already know that if this is the feature of a person, this is the credit history of the person. Based on that, they will also give you that, okay, he paid, he didn't paid, he paid, didn't paid, right? and based on that you adjust your model, right? So there also you have a x and y with you. You will have your x and y with you at that particular instance also. Okay, so everybody gets this this function thing, right? That's how this function is working. This function f is called the affine. So the f function that you see, this is called the affine thing, and it's doing nothing, right? You saw that this is it's doing a linear thing here. We're just multiplying the weights to the corresponding x1 x2, and you might now consider x1 x2 as the importance feature. So the more important x1 is, the more higher the value of w1 will be, right? The more lower the value of w2 is, it means it doesn't make much sense to y. So everything that we will now talk will be with respect to y. So the x2 is not making much sense to y, so the value of w2 will be very less. Let's say y is dependent on x1, so this value of w1 will go more higher, right? And then your bias you already have, this is a static thing, right? Because the x not associated to it is equal to 1, right? Let's now go back at what further happens here. Now you get the y out of here, right? Now this y thing is a little, you have got the answer, and this might be greater than 1 or less than 1 also, right? So there is no measure of this answer. It might happen that w1 w2 is very small. Let's say w1 w2 are very small, then the value of y might be almost equal to 0, right? Or let's say that w1 value is very high, like very high, so the value of y might also get very high, right? So now this might bring some bias, this might bring some ambiguity to our model. This y might be sometimes, next to infinite, it might be equal to infinite, or it might also be equal to 0, right? Depending on the variables. And we don't want that. We want our y to be in some particular range, right? We want our y to be in some bonded weights, right? Then comes next guys whose names are activation functions. Activation functions. Now we got to know that how this y is made, right? How this y is ultimately achieved. Now to adjust the value or squeeze the value of y, we need some other thing, right? We need something that can control the value of y, and these are called activation functions. Now what activation functions does is that they will take the value of y and they will squeeze the value of y in some certain range. What they will do, they will squeeze the value of y in some certain range. So we have multiple, let's say we have a step function, we have a 10h function.
Shivam, Sanjay this side. Can you please come again about this activation function? Not getting you properly.
So let's come back what this activation function is. So you understand that the value of y, how it is calculated, right? It is now totally dependent on w1 and w2. If the value of w1 and w2 is very less, I mean 0.0000, or let's say 10 to the power minus 23, then the y is going to be very less, right? Next to 0. Or let's say that the value of w1 and w2 is like 10 to the power positive 48 plus 48. So this might be very high. The value of y might be very high. There might be no standard to control this value of y, right? Mathematically, there is no, this value can go from negative infinite to positive infinite, right? And this is not a very good range to get about a particular output, right? So what we do is we introduce something that is called activation functions. Now what this activation function will do is activation function will make sure that your output that you have got y should be in some particular range. What it should be? It should be in some particular range. Now how do you decide that who is going to be in what range, and how is that range called? See, the activation function, if I ask you mathematically, the mathematical purpose of introducing an activation function is to squeeze the value of y between some variable called 0 to 1, right? Majority times. So the value, so the purpose of activation function is to bound the y in some range, right? And this range might be -1, say 1, 0 to 1, or sometimes 0 to infinite. It might be different things, right? I was at this thing that mathematically the value is to be squeezed between 0 to 1. But if I talk to you about statistically why I am doing this is, now imagine till here, till this particular range, your model is a linear model. Everybody agrees with me, right? This is a linear model. Nothing non-linear have been done till now, right? All the things that we have done till this step in this circle, everything is linear. There is no non-linear thing, right? Now, linear things are a little bad at classifying things if there are more than three classes, right? If I ask you, can you, if let's say there are three classes, one is like crosses, right? One is circles, right? And one is some triangles. Now, can you make a single line and can divide these three data? No, right? If it would have been two classes, you might have, drawn a single line and you might have divided the data into like two classes, right? But if it is a three class data, how will you divide this? You have to ultimately make a triangle kind of a shape or this kind of a shape, right? Then only you can divide the divide this thing, right? So I'll show you a photo also. Let's say, let me give you an example, then I'll show you how this works. Okay, can any one of you, let me hide it here. Now this is this thing in front of you. Everybody can see your data. There is this red dots and there is a blue triangle in the screen, right? Everybody can see this. Now, can you make a linear model that can separate these two things? This can only do in a two dimension, right? But if I say you that, okay, see a magic, anybody wants to try this thing? How will you do? No? Okay. What I'll do is I'll remove this now. So what I did was I introduced a third dimension, and now I could easily separate by introducing a hyperplane here, and then I can say, okay, something that is above this hyperplane is red, something that is below this hyperplane is blue. Makes sense to everyone, right? So this is why we do activation function, to make sure that we want to classify things more better, to make things more clear. We do a activation function. So mathematically, why we are doing activation function? Because we want to squeeze the value of y somewhere. But if I talk statistically, what we are doing, we are introducing non-linearity in a linear model, because linear models are very much not capable of classifying things in when the number of classes increases. So now we saw that as soon as we increase the linearity, if we increase the dimension in the data, if we introduce non-linearity in the data, what it is doing? It increases the chances of making a linear separable model, right? Right. So if I say in three times, first mathematically squeezing the y. Second, if I say graphical thing, why we are doing this? Because we want to introduce a new dimension. And statistically saying why we are doing this? Because we want to introduce non-linearity inside it. Now you might be asking what these functions do. It's a very good question. I have activation functions graphs. See, this is how a sigmoid looks like, a tanh looks like, a ReLU looks like. And see, everybody is bounding. So see, sigmoid is bounding between 0 to 1, tanh is bounding between -1 say 1, ReLU is bounding from 0 to infinite. So it lets go everything that is going above. Yes, we have step function also. Step function says that you can go if something can be only have two things, either 0 or 1. If something is negative, it goes 0. If something is positive, it goes 1. It's a step function, sigmoid, 10h, ReLU. So there are multiple things. These are doing the same thing that we want to do for a activation function. ReLU, you can understand that if something is negative, it says it's a 0. And if something is positive, it lets go whatever the value of this is, right? I write the variables in here. This is what brings in. Sigmoid is this, tangent is this, and ReLU is this, right? What is the maximum of 0 to 1? That ever value it will take, right? This is what activation functions is. Let's say that you have this thing called y1 and y2, right? And now the value of y1 and y2 is very large, right? So this y3 will become ultimately also very large, and this y4 will become also very large. And we know this is not the exact thing. We always expect our output to be in the form of 0 to 1 if it is a classification problem, and if it is regression problem, then it will always be in some range from 0 to 1, right? You all agree with me, right? In machine learning also, whenever you did a classification problem, you one hot encoded the problem. So you never said that the output is going to be a C80 cat or DOG dog, right? You always said that, okay, if 0 comes, this is cat, 1 comes, then it's a dog, right? You did the same thing, right? In machine learning also. Or if it was a regression problem, then you always regress a value from 0 to 1 with a multiplicative factor, right? So this is what is happening here also. The y3 and y4 ka value can never go up beyond a limit. To control that limit, we have to squeeze the value. And see, when I'm saying squeezing the value, that is in mathematical format. But if you see in statistically, what we are doing is that we have to introduce non-linearity into the data, right? Because linear data are not linear equations are not good in separating non-linear data, right? Right? This becomes separable. You see, now it is very much separable just by a simple hyperplane. Okay, so coming back to a feed-forward neural network. So see, this was the input x1, this was input x2, and now what a feed-forward neural network expects is that a hidden node should be connected to all the inputs. What does it expect? It should be connected to all the inputs that are in the previous layer. So this is, let's say this is called layer, input layer. Wherever your hidden neurons, this is called hidden layer. And your outputs are here. This is called the output layer. Now, when you are building this feed forward neural network, your responsibility is just one, that whichever neuron you're standing, let's say we are standing on this particular neuron, let's say this neuron, this neuron. Now the only thing that this is not a neuron exactly. Oh, sorry. Let's say we are standing on this neuron. Now the responsibility is just this, that if you go to the previous layer is the input layer, all the neurons in this layer should be connected to this hidden node, right? Similarly, output 2 also expects the same. You go to the previous layer. So this is the output layer. What is the previous layer? Hidden layer. So all the neurons in the hidden layer should be connected to the output node 2. Make sense? Or if I make it more easily, let's say that whichever neuron you are standing, just go to the previous layer, and all the neurons in that previous layer should be connected to this particular neuron, right?
What is this layer signifying here?
Correct. Very good question. So what you are doing is you have stacked all your neurons one by one in some format, right? So all your input neurons. So see, whatever you made in this above statement here, in this above thing here. So this x1 and x2, this is x1, x2. This might be x3, x4, x5, x10, right? So these x1 and x2s are what? Inputs, right? So what you do is you collect all these and you just put it inside a layer here. This becomes a hidden layer. Now you will not only have one neuron, you will have multiple neurons, right? So what is happening is that what you have done is, rather than having just one neuron, what you have done is you have made multi-neuron system. So this is a feed forward multi-neuron model here. So what you're seeing in the previous photo that was the image that I showed you, that was just a multi-input single neuron, but now you have multiple neurons. So what you do is you stack these neurons in this layer, then you can have, so this is just an example. What you can do is you can have an image like this also, multi-layer. Okay, so now if you see Tarun here, so what is happening is these are your inputs x1, x2, x3, x4, right? This is your input layer. This is your hidden layer 1, where all your affines and activations are happening, right? This is your layer 2. Again, all the affines and your activations are happening, and this is your output layer, hidden layer HL2. This is HL1, and this is input layer. So what is happening is that, let's say this is called neuron 1, that Y1 just marked. So let's say this is N1. This is called neuron 1. Now what is happening is that this neuron 1 is connected to X1 also, X2 also, X3 also, and some bias also. So what is happening here? This affine will be happening here. What will be happening? It will be here that W1 X1 plus W2 X2 plus W3 X3 plus some bias B will give some output called Y. And here you will be having a very small activation function also residing here, right? Similarly for this N2 also, this N2 is connected to all the inputs, right? This N2 is connected to all the inputs. This N2 is connected now. It is connected to this, to this, to this, and this. Now N2 will also do some affine and then bring some activation, small activation function here, and it will also give some output called Y2. Similarly, Y3 will also be here. Now this Y1, Y2, Y3 will become input for these neurons. Let's say we call this neuron as N4. Now this N4 is connected to this, this, and this. Similarly, again affine, and let's say it gives the output called O1. Now O1 is here, similarly O2 is here. Now this O1, O2 will also become input for this, let's say we call it O1 right here, right? This is O1. Y4. Let me remove this. Sorry. We were here that there is this some output called Y4, and there is some output called Y5, right? Now what is happening? Y4 and Y5 will become output for this O neuron, and they will give some output O1 and O2 similarly here, and then you will have outputs, right? This is how a multi-layer neural network works.
How will we know that how many layers?
Correct. This is one of the very good questions that first of all, how many layers do you want? This is the layers that you have, L1 and L2. Now you might have another question that, okay, in one layer, how many neurons can I fit? So there are currently 4. I can fit 5, 6, 10 also, right? I can fit 10 neurons also. So who is going to tell me that how many neurons and how many layers? This is what data science you are going to do here. I mean, everything is built for you. This neuron thing and this all thing this is already built for you. The only thing that you have to do is that you have to come up with the optimal number of neurons and optimal number of layers for each neural network. And now who is going to decide this? Very good question. This is you who is going to decide this. And how? Okay. So first answer is that hit and try, that everybody will tell you, and I am also telling you that the first approach is hit and try. Let's say that you are doing a very new problem. I mean, you don't have any idea, you are just doing. So one thing is that you'll go with the hit and trial model. Second is that as soon as you become a little bit expert, now you start learning, okay, this is how my model is reacting to this particular neural network layer, then you see the model capacity. Okay, so let's say that, so see, this is a very good question, but this is also an advanced question. Now see, when this, let's say this is called neuron 1. When this neuron 1 is connected to x1, x2, x3, there is a weight called W1, W2 on this layer, and W3 here, right? So But when this N2 is connected, this is not W1, W2, W3. There is W4, W5, W6. So when this X1 is connected to this N2 here on this line, there is another weight, that is W4. So imagine how many weights are there for 3 inputs, 3 neurons. There will be 9 weights, right? Now there are 9 weights. Now imagine here again that you have 3 inputs and 2 outputs, 3 to the 6, then you have 6. So 9 plus 6. Then again here 2 to the 4. So you will have 2 plus 4. So 9 plus 6 plus 4 is 19. So 19 weights are there, and then you will have 3 biases here, right? So 19 plus 3 is what? 22. So for the small neural network, you have 22 values that you have to predict, right? Because y1, w1, w2 we have taken as what? As random, right? And biases are also random. So you have to adjust them in a very optimal way so that you can get the output as y. So now imagine that you have 22 things that you have to train here. 22 things that you have to predict, not predict, but you have to optimize, right? And now let's say that you have a data only for like 10 rows. Now, does this justify that you will have 22 things to adjust in the 10 rows of data? So this is called capacity building. So what you have to do is that you have to check your model if your model is even capable, if the data is even capable to adjust these values, right? Let's say that you are just doing a simple addition, right? If you give two numbers, your model has to give some output, right? Now let's say that you have 1,000 examples for it, but now you're building a like say 1,000 layer and 1,000 neuron per layer, 1,000 neurons, and then you have 1,000 layers. Now does the model require this much of data? No. The data will be lost in some third or fourth layer only, right? And see what I just said in just last 2-3 sentences. This will come slowly, slowly, slowly with the experience in you also. So what you'll do, so whenever a new problem comes to me, I first of all read the research paper through it. See, because we are not researchers. Let me be frank with you. We are not researchers who are going to make things. We are deep learning engineers here, right? We have to implement the engineer and we have to solve a business problem through it, right? So what you do is first of all you read some papers out of it, right? Then you get the intuition of how do you build a neural network around it. Then I do some hit and trial error. Okay, this is how you build and this some changes. And then slowly you understand, okay, when I change this thing is affected more. Then you reduce and more. Then you have some prior knowledge also like that I told you. Keep capacity, that what is the capacity of the model. Let's say that you have a very large data, but you are just building one layer. Then the data is underfitted, right? Or let's say that you have very less data, but you have made a very big neural network for this. And this is called overfitting, right? You have a very over number of neurons for your model to be predictable, right? So slowly you will you will have intuitions. And this is, I will tell you, with your when you will be doing your first problem in a neural network, you will understand slowly. See, you might be thinking that I'm not taking to you practical, right? I am not telling you about any real world example, but this theory is really important. I might directly jump to the code also, but that will make no sense to you after 2 or 3 weeks, right? Because code anybody can write until unless you don't know, okay, what will happen in the next after 2 or 3 months when you will be making your own neural network, you will fail that, okay, which activation function to use. Then this thing will occur. Okay, so see, this is what he is talking about to all the people. This is what he's talking about. Let's say that you want to add more layers. So currently there is only 2 hidden layers. You want to add more, add more, add more, right? If you want to increase per layer, you want to increase the neuron, you might go like this also. Okay, you might like, I'll reduce it to like, let's say 6. This I'll reduce it to 4. This and 2 and this is 1, right? This is how your neural network will look like. These are the 2 inputs. Now every input is connected to the every neuron in the first hidden layer, right? Then second, then third, and fourth similarly. And this is how the data is flowing inside here. You can see now slowly. When we put every X into each neuron, does every neuron give same Y? Very good question. But no. See, Kim, if we come here, it would have been the same if they would have same W, right? So if X1 is connected to N1 here at this layer, it has W11. right? But when x1 is connected to n2 here, it has something called w12, right? So there are different weights. So it is coming from x1, but because it is connected to different neurons, different input neurons, they will have different weights also. Understandable? So to other people, what Khem is asking is that, okay, that you are doing affine. I understand that you are doing affine, but let's say that, let's go back to affine equation. Because the value of x1 and x2 is constant, the output will always be constant, right? But no, because y1 is made up of this equation, and this equation is also driven by w1 and w2, and the w1 and w2 values are different, the value of y will also be different in each case, right? Makes sense, right? And when we were asking about a real world problem, this is how a neuron will work. Okay, I have this also, don't worry.
So you mentioned overfitting and underfitting neurons,
Yes,
so how do we come to know that based on the Y or
again a very good question. So I took these two words called underfitting and overfitting. This is how it actually works. This is a intuitive GIF. Okay. So what Suresh is asking is that, that I took two words in overfitting and underfitting, and how do we address this problem? So what we do is that we divide our data into two parts, and I think you must have also done this in ML also, right? Training data and validation data, right? Not two, just three parts, right? Training, validation, and testing, right? So what you do is whenever you are training your model, you just make a slice, another slice of data, and this is called validation data. And you will never show this data to the model, right? So no, you are never going to train your model on this particular data. So what you're doing is you will never show this data to the model, so model will never come to know about it. So it will never learn about it also. Now once your model is made, what you will do is you will test it on this data. What you will do? You will test this on this data, and then the model will say, okay, this is how it looks like. Okay, this is what the predictions are, and then you'll see the predictions, and then you'll compare the predictions. Okay, this is not what I wanted, so the model is underfitting or overfitting. Now how will you do underfitting and overfitting? You'll do a confusion matrix, and then you'll see that if the model is just giving out you only one classes, let's say that your data had 10 classes, and if the model is just pushing towards one class, then this is overfitting. Your model is overfitted at a very lot level. Okay, then we have another question from Game. He says that it means now this dog image, when we expand this image mathematically, this will come out to be three things. One is called x1, x2, and x3, right? Now what we have to do is this x1, x2, x3 is done towards from our end. Now this x1, x2, x3 is connected to this neuron 1. Okay. Now x1 is connected to n1. This is called w11. But when it is connected to n2, it will have some another random weight called w12. W12. Make sense? So number of neurons you can increase as much as you want. As much. You can have n3, n4, n5, n6, n7. Doesn't matter. But you have to make sure that this w11 is not the same weight for all n1, n2, n3. Right? Cool. Thank you. Thank you. So inside the matrix, you can see there are multiple values. The value ranges from 0 to 255. 255 is for like utter black and 0 is for white. Right? The value ranges from 0 to 255. You can see the more black it is, the more the value it has. Right? So what is happening is that these are the multiple inputs that you will have inside your images. Multiple inputs, and all these inputs will go in here. So in this particular example, you are seeing 3, but this time you will have more. So these all the zeros in first, all the values in second, third, fourth, fifth row till the 28th row. You will have all the numbers inside this input layer stacked one by one. So ultimately you will have 28 cross 28 is equal to 784. So you will have 784 inputs normally for this small image. And this is you guys were all asking about me how this will work in real world. So real world, let's say that you have an image of 500 cross 500. So that becomes around like 25 0000. That means 2.5 million inputs you will have for single image, right? And let's say that you have 10,000 images, so this becomes multiplied by 10,000, right? So these are the number of inputs that will go inside one by one by one by one by one. So one image will go one time, two image will go two, second time, third time, and then based on this, the output is the model is going to do some calculations in the hidden layer, and then it's going to predict the output, and it will give you some output at y. Okay, so now we'll turn up pages and we'll move to multi-layer perceptron. But now we might have multi-layer perceptron architecture. Now a multi-layer perceptron architecture simply means that you might have multiple hidden layers. Okay, so apart from having a input layer and output layer, you might have hidden layers in between of them also. Whereas a single perceptron was only a linear function, a multi-layer perceptron will have multiple linear and non-linear functions, a combination of them, right? I'll show you this. Again, I was not able to continue today and tomorrow. Today also you will not be able to continue. Okay, don't worry. I'll push the notebook in there and then you can have it. Okay, so I think you already saw this, but I have an image of multi-layer perceptron also. Let me show you. Okay, so this is how a multi-layer perceptron looks like. If I just minimize my screen a little bit, so you can see this now. Again, just to memorize things up, this is x1. This is what your input, x1, x2. These are your two inputs, right? Now you have a single hidden layer right now here. You have this one neuron here. Now you already know that what is the calculation going on inside. There is the affine function. Affine function, what it does, it takes input from all the behind layer neurons, right? So if I say it takes input from all the behind layer neurons, and if this is a hidden layer h1, then it means that it will take inputs from all the neurons inside this input layer, right? So this is x1, then this is connected, this is x2, this is also connected. Now whenever a neuron is connected to another neuron, it is connected through some weightage corresponding to it, right? Let's say this is w1, this is w2, right? And then you might also have a x naught. Now the x naught is always equal to 1. So you might say this is just a bias as b. Now this b is like constant to this neuron also and to this also, right? I change this and it must have come to this. Okay, so now this is x1 and x2. For this, when they are connected to this neuron, the one that is downwards, and this neuron, they are connected again to some weightage, but this weightage might or might not be equal to the w1 that is the one that is described here. The one described here, this is never going to be equal to this one, right? So these are different weights associated different. So you might, to make it more simplified, you might think that whenever there is a string connecting two neurons, it is connected through a weightage, and this weightage is different for each one, right? This weightage is different for each one. You might also see the equation here down here, w naught in plus 1 plus w1 x1 w2 x2. Now you know that w naught is equal to 1, so we have replaced w naught is equal to 1. Sorry, x naught is equal to 1, so we have replaced x naught with 1, and w naught in itself, you can say w naught, or what people like to say is it's called as notation called b, and this is called the bias of the neural network. Okay, bias, and these w's are called the weightages, right? And then you do again a summation out here, and this time you do the final output, and then you give the output right here, right? You also remember that after every neuron there is also activation function which is sitting here, here, and here. They are also present on the outer section also. This and this, they're present here also. So they, and then you read that there are different types of activation functions. from step function to sigmoid, then to uh, softmax. We have different. I'll slowly go through each of them, and then you'll understand that how they interact and how you might be also changing them according to your needs. Right? Okay, I'll minimize it. Visible now? So now once we are done with this perceptron layer, now okay. So this is called a feed forward neural network. Just one thing, feed forward neural network. Once you come from here, this neuron, you go till here, then there's some calculations goes on. Then you come to here, which is taking connections from this and this neuron, and then you give the output, right? Now let's say the output comes out to be some y1, whereas the actual output was, let's say, y, right? Now there is a error associated to it. So you say that you have a error, and what is the error? Y minus y1. This is the error, right? Y was the actual answer that should come, right? But you are saying the answer is y1. Then y minus y1 is actually the error. What it is? It is actually the error. This is actually the error, y minus y1. Now your model, you say to your model that model, you have done some kind of mistakes. Now if you go back inside your session, if you go back to your session, you might see some errors inside it, and that error might be equal to y minus y1. So go and do the changes. Now if you see our function that we have done till now, the result through which we have come till now here at this point y1, it is all how much dynamic things you have taken, I mean non-static things you have taken. See, x1 is always going to be static, right? This no one is going to change this x1 and x2 because these are given by the data itself, right? So the data can never change itself. It is you who has to change, right? Then what is the thing that we have taken assumed? These are the values of w1 and w2, w1, w2, and w0. These are the similarly these w's here. I mean all the w's that are here, all the w's that are here, these values are something that you have assumed, right? So now what the model says, the model says that the value that you have assumed, W1 and W1, W0, W till Wn, these values might have some kind of a correction because the current values of W are giving some error, that is y minus y1. So to reduce this error, you go back and check your values of W and switch the values of W to such an extent so that they minimize this error, right? Whatever I said just now statistically, right? Makes sense to everyone, right? What I just said here. Okay. Now this thing is called backpropagation. Back. Now this thing is called backpropagation. Now backpropagation, if I take the copy of thing, can we try different activation functions too? Yes, you might try whatever activation functions you want to try, but there are some. Okay, so Oman has asked this question that how do can we use different activation functions also? Yes, it depends on the problem that uh, uh, what functions do you want to choose. So I'll tell you my particular example. So I was working on this library that is called DOLD5. Here what we are trying to do is that we are trying to restore colors into uh, images that don't have color. So I mean if you talk about images that are like from that are before 1924. So we have some German artifacts. Those are before 1924, and those are totally black and white images to us, right? So what we have to do is that we have to fill images inside it. Now, filling images inside it is, I'll tell you, it's a complex process, but there is a form of images that comes out. That is called the LAB images. So if someone of you who has interest in photography uh, or if you understand what images are, then you might have heard this term called LAB. LAB images to convert. Now the range of LAB images is from minus 128 to 128. So here my task. So if generally if you see the activation function, if you remember from the previous class, all our activation function from ranging something from 0 to 1 or minus 1 to plus 1, right? Now I wanted something that has to go from minus 128 till plus 128, right? Then how will these things two go? So accordingly, you can change your activation function and you make your own function out of it, right? Make sense?
Yeah, I forgot you in last lecture you said whenever you're trying to bound your values in a certain point, then you use
Correct,
different activation function. I just reminded.
correct. Totally correct. So this is all about the feed forward. Now, so feed forward, if I just say in one line, feed forward is going from input to output. Now, if you want to come back from output to input to make corrections, that is called back propagation. Now, back propagation is one of the most used, or I should say, okay, now visible. Okay, now this is one of the most not used, but this is one of the most obvious things in backpropagation. This is in AI, and why this is famous, because this is the main backbone for AI. This is how AI learns itself, right? So people say that AI is learning from itself. No, it's not learning from itself. It's learning from the errors. Whatever error it is making, it goes back and it checks. So see, a human tendency of error checking is what? Let's say that you are doing some calculation and you do some error. What do? You go back again to the calculations and you check, okay, I did this mistake, and then you correct it, right? This is also the way how machine is also understanding. So what machine does, machine does some calculation, it calculates that there is some error, then based on the assumptions that it took, or based on the assumptions it took, it thinks, okay, these are the things I assumed and this is now the error. So what it does, it goes back and say, okay, I will change my assumptions, I'll tweak my assumptions, and then I'll see what is the error again. This is a iterative process. So again, let's say that in backpropagation, what will it do? It will try to change the values of W1 and W2, right? It will try to change these values of W1 and W2, and then it will again go in the forward direction, and it will again see, okay, again there will be some error, but this time the error will be less as corresponding to the previous error, right? Now again it will go back, then come forward, again go back, forward, go forward, inward, forward, backward. This will happen multiple times, and at one point the error will saturate. The error will look like this. So error graph will look almost like this. Here error is on the y-axis, right? And this is whatever you say, time on the number of epochs or steps, let's say, as of now. Steps means that how many times you have gone forward, backward, forward, backward. So you can easily see here that that the error was very high at this particular point, but then it slowly decreased. It decreased till here, but now it's almost saturating. So it's like almost saturating, and at one instance it will be like parallel to the x-axis. It will become parallel to your x-axis. This is how it looks, right?
Shivam, so how this program will go back and forth? Means it's APIs, or we have to manually do this every time, run the program each time, and or run the program in the reverse order? Can you make it clear?
Okay. So uh, so so uh, so the point is that first of all we'll do it on in our hands. So we'll do it manually first.
Okay.
But good news for you is that no, you don't have to do it manually. All these things are like handled by the framework itself.
Many times we have to go back and forth so that it is
No,
minimized,
no,
the
no,
error
no.
become
This you have
parallel.
to decide. This you have to decide. You'll see the error graph continuously, and then you'll decide, okay, now I want to stop, or okay, no, I want to go further. This is up to your hands. Okay, makes sense, right? I mean, see,
Correct.
what if they can even tell this, that if they can even tell this that how to stop, then I think the problem is done. I mean, then we will be doing nothing, right? We just open and we just say this is the code, read the code and do it itself. Read the problem and do it itself, right? No. The problem is that it will do everything, all the calculations for you, but the mind, where to stop the problem, where to go ahead with the problem, is still in your hands. You have to still make sure that where do you want to stop the things, or where do you want to again get the further out of it, right? Make sense, right? Okay, let's move forward. I have one more theory for you. Let me paste it. Okay, so don't read this. I'll tell you. This is just for your purpose, so that in the weekend, when you weekdays, when you go back and you want to, don't have to like revisit the whole video. Don't review the video. You can just read it through the notebooks only, right? That's why I'm just copy pasting the theory here also. So what happens is, I've already told you that all the edges that you are hit, that you see here, that all these lines that you, sorry, all these lines that you see here, these lines, these are called edges. All the connecting things are called edges. Now for every corresponding edge you have a weightage, right? For every corresponding edge you have a weightage, and these weightages are by default randomly assigned to you, right? Now they're randomly assigned at the very first point. When the problem start at that particular instance, these are like randomly assigned to you. Now for every input in the training data, the ANN is activated, and its output is observed. This is what I told you also, right? That once we'll do all the calculations, we'll do the first feed forward neural network. We'll check what the output is, and then the output is compared with the desired output that we already know. And the already know, this is also, you might have heard this term again and again. This is called ground truth, right? So see, deep learning may, you might have heard, this is not equal to what traditional technologies. In traditional programming, you have been given the input and people ask you output. But here it's not like that. Here they will give you the input also and the output also. And then you have to define some way to convert this input into output, right? This is how machine learning works, right? Because they give you input also and then they give you output also. So like say, let's first, on the first example, if someone tells you that you have to do some image classification problem, then this is not like they'll give you at the very first instance, this is the image, now tell me what it is. No, they'll give you a training data set where they will give you the output also. With the image, they will also tell you that, okay, 9 is written here, 5 is written here, 7 is written here, right? So you have the ground truths with you also. Now what you'll do, you'll compare your result with the ground output, and then the error is propagated back to the previous layer. If you read the line propagated previous layer, the error is noted and the weights are adjusted accordingly. This process is repeated till the output error is a predetermined threshold value, or where you think that it is being saturated. Right? This is what I also told you. Now, if I tell you that how it goes, okay, let's see one by one. Mathematically, I'll show you one by one also. Now see, it's pure maths, okay? Just a little attention and then we'll be here. Let's say this thing is called, okay, or otherwise what I can do is, I'll just pick up the smaller problem and then I'll show you also how it is done. Okay, just a second, let me search for the image that I have. Mhm. Okay, sorry, I cannot find it right now, otherwise, but okay, let's go. Let's see that error is equal to, I'll write it down. Error is equal to, let's say, y actual minus y predicted, right? Let us write down error is equal to this. I'll write down. Okay, now if you see that how is this y1 calculated, then let's say that we had an input called we had an input called I1 and let's say I2, write down, and let's say that we only have this one. Okay, let's make it more simple, right? I will take just this image. That will make you understand how things work, right? Let's copy this. Okay, I'll write it down. Okay, this is the example, right? So now we have input as x1 and x2, right? And we have an output called y. Let's say that the actual or the desired output be ya, right? This is what we require from them. This is how we have, and the value of y is equal to w1 into x1 plus w2 into x2, right? Everybody agrees to this, right? That how is this calculated, right? Now the okay, and let's then define error. Error is equal to y minus ya, right? Or whatever you want to say, ya minus y doesn't make much problem to us, right? This is how this is working. So now if I say E is equal to y minus ya, then I can say E is equal to, instead of y I can write w1 into x1 plus w2 into x2 minus ya, right? Now if you open up this, doesn't make much sense, but let me write it down. W1 into x1 plus w2 into x2 minus ya, right? Now sorry. Okay, now the error is this, right? Now what do you want to do? Now the final equation of error is in front of you, right? If I write it down, the final equation is in front of you. You can now you have the final equation in front of you. Now you have to see that how to minimize this equation, right? How will you minimize this equation? This is the equation of error in front of you. Now what you can do is, now you might be thinking that okay, this error equation is just a simple linear equation, I can solve it linearly. Now imagine that instead of x1 x2 you have 1000 xn, right? Now this equation is not a 2D equation. Now this is a 1000 dimension equation. Now you cannot just simply do things and just check it around, right? You cannot just do it like that. You cannot just plot a graph and you can look into that, right? This is a little more complex than we thought of it, right? If I show you how the graph might look like, right? The graph will look like this. Don't just read this, just for the time being, forget this thing. Just don't read these things. Okay, so what I can do is I say okay, this is your error equation, or let's say error I can also say j of w. You might see this terminology j of w as error. Okay, I should not do this. This is not making it good. Okay, when you plot this thing here, now what you can see is, see, x1 is what? X1 is x1 is a constant, right? x2 is a constant and y is a constant. You all agree, right? That x1, I will put a star and say x1 comma x2 and ya are constants, right? You cannot change them. These are constants, right? They make no effect to e. The one that might change e is w1 or w2. Okay, for a fact, none of you told me, but we missed a bias also here. Bias b. We missed this bias b here, right? Say this b, but this b is, I mean, it's not going to make some effect to us, but still, just for the courtesy, let's put this, right? To anyone, any doubt is still here, please ask me questions, right? So now we can see that, okay, what is happening is that E is only dependent on W's, right? The error is only dependent on W1 and W2 and B. None of the other people are changing this E. So what we'll do is we'll try to plot this error with respect to the weight, and we'll see this is how the graph looks like. And what do we want to do with the error? If error is ya minus ya, what is our aim? Our aim is to make ya is equal to ya as equal to y, right? This is what our aim is, right? If ya is equal to, then we are saying that the error should be equal to 0, right? Error should be equal to 0 or tending towards 0, right? But if I say mathematically 0 is, if I say statistically, this error is never going to be 0, right? This is never ever tending to 0. So what our main focus is? Our main focus is that if E is here, our main motto is to minimize the current error. Whatever the error is, we have to minimize this error. Now the value of this error can be found here, right? You can simply see the graph and say, okay, this is the value of E. Just take the value of W's and plot them, right? But as I told you, now these errors are not just two inputs. We have like 1,000 inputs, so we might have 1,000 W1s and then one B also. So we cannot just plot it. So it will become a 1,001 dimensional graph. You cannot just plot it. So now we have to think mathematically that how can we minimize the error E. Now minimizing the error E, but we also have the like the equation of E also. We have the equation. Don't think that we have the graph, just think that we have a equation of E also, right? This is above, right? An equation of E is somewhat like this. If I copy this from here, this is somewhat like this, right? This is somewhat like this. This is what the equation of E is, and this is how we have to minimize. Now in mathematics, we have learned, in inferential mathematics, we have learned that if you want to minimize any curve, if you want to minimize any polynomial curve of the order greater than 2, what is the process? Can anybody tell me? If you want to find out, if you want to know that where is,
First
yeah,
derivative, I believe.
I'm sorry, what?
Take the first derivative
Take
of
the
that
first
curve.
derivative. Okay,
Yep.
okay, correct. Take the first derivative. That's very much correct. So as Omar said, that you have to take. So see what the first derivative tells you. The first derivative tells you that wherever there is a change in the slope of the graph. If I talk about what we learned in our higher education about differentiation, was the differentiation tells you that point coordinate where the graph changes its slope from positive to negative or negative to positive. So if you take the first derivative, it will tell you this place. See, it was in negative slope, then it came in positive slope. Now again here, when it was in positive slope, then it came into negative slope. Again positive, negative, positive, negative, positive, negative, positive, negative. So it will tell you all the places where it has uh, changed the slope from positive to negative or negative to positive. Vice versa, it's possible, right?
Yeah, but
Sorry.
like for global minimum and maximum, you have to take the second derivative instead of the
Second
derivative.
derivative. Correct. So this was how we talk about inferential mathematics. But if you go in descriptive mathematics, it says that what is a derivative of a function? A derivative of a function when you have a tangent that is parallel to the x-axis, right? When it is parallel to the x-axis. So how where will be the tangent parallel to x-axis? Whenever there is a slope that is equal to 0. So if the slope was from positive to going to negative or negative to positive. So both the mathematical percepts tells you that there is a change in the slope in that, right? So similarly, we can know that where are the positions, where are the places where we can get a change in the slope. Now, as Omar very he suggested that we will get all the points where it is maximum and minimum also, and we just want the point where it is minimum. I mean these points, we are interested in the one that are by dotted by green, either this, either this, either this, right? But now again there's a problem is that these are very higher error. This one that I'm just marked as E1, this is a very higher level of error, right? We don't want a higher level of error, we want a lower level. This one we want the E3, we want E3 to be our error. So what we do, we take double differentiation. We first take differentiation, then we take double differentiation. Now double differentiation, then Omar, can you tell me what is the condition? If it is less than equal to or equal to less than 2. Okay, I'll tell. Now with the first derivative you can know that where is the slope of change, but if you want to know that what it is, if it is a maxima or if it is a minima, how do you know it? You know by doing a double differentiation of that thing and then checking its dimension. So if the double derivative of any of your function is greater than 0, if the double derivation of a function is greater than 0, then it is a minima, right? And if the double derivation of any of your function is less than 0, then that is maxima. These are the conditions. Then you will check accordingly and you will go for minima. Now again the problem is that okay, now you will reject these points. You will reject all okay. So you might discard this, you might discard this, you might discard this, you might also discard this, right? So you will remove all these blue points. Now you will only have the green points with you, right? Now you want this E3 to be there, right? Now we don't have any mechanism through which we know that we have reached global minima or not. This is the dilemma in deep learning. And so slowly what we do is now understand this mechanism. This is called this whole thing that I'm showing you right now is called gradient descent or GD, right? You might have also heard this as SGD, stochastic gradient descent. When you do a gradient descent in batches, it is called stochastic gradient descent. Okay, I'll take a pause here, and to anyone who has not understood this thing, please ask. I know I might have taken a very quickly this up, and again one more point to other people also who are not math heavy. See, this maths is just for your understanding. You won't be doing all this maths in your programming. No, you won't be doing all this in your deep learning courses. You will be just writing the direct code. You won't be doing all this mathematics. This is already done by the framework, so don't worry about this. But again my point is, please try to get this inside, because this is necessary, right? This is necessary. If you don't understand what is your framework doing, then there is no sense of your framework doing something, right? So so just please and if you have any doubts, please ask, do not hesitate, because I know it took me 3 days to understand this thing. So I was how do you put okay, so I am assuming that everybody understands still here. Okay, so what I'll do is I'll take the first derivative of dE, sorry, dE. Now you know that E is equal to this. Let's write it down. So now you have seen this one thing that the E is dependent on either W1 or W2. So what you will do is you will take the derivative with respect to one time with respect to dW1. So what will happen? It will say x1 and then everything is equal to 0, right? Because these are all constants. Am I correct or wrong? What I'm doing is I'm trying to take a derivative with respect to W1. What will happen? X1, correct. X1 into 1, totally correct. Plus W2 is again a constant plus constant plus constant. Makes no sense, right? That's there. And if you want dE by dW2, then what will happen? It will give you x2, right? x2 into 1. Don't worry again to, okay, it's in chat. Just a second. Again, see, someone is asking me this question that, is this really required? No, this is not required. This is just for your reference. Don't worry.
Shivam, I think
Okay.
you need to add a constant term too into the derivative.
Oh yes. So we need we add a constant term, but here we know that that constant term is equal to 0. So yes, he's right. We'll have some C1, C2, but these are constant as of now for us. They don't bring much value to us. I'll put this picture around. So see, this was just for one, right? If you go from here till here, this was just for adjusting the new values. Now what will be the adjusting values of W1 and W2? So now we already have the older values of W1, W2. So the new value of W1, W2 will be dW is equal to W1 minus dE by dW1. And W2 will be equal to W2 minus dE by dW2, right? This will be equal to this, and but there is a special term that is called alpha that is associated here. It is multiplied here. I'll tell you what alpha is here. I don't know how to type alpha in like latex, but okay. Okay, so now you might ask that, okay, now we understand that this is the new value of W1 and W2, right? So now what will happen? This older value of W1 and W2 will be replaced by the new one, and then you again go forward, and then you again get the error, again come back, change the value, again go forward, backward, forward, backward. But there is one thing that you might ask me, that what is this A here? This A is called alpha. Sorry, this is not A, this is actually alpha, and this is also called as learning rate, or you might see people calling as LR. Right, now what learning rate is, now just pay a little attention towards here, right? So let's say the previous value of W1 and W2 will give you some error that would be here at this point, the one that I draw very small here, right? The next one will be here, then here, then here. So it might vary that how gradually you are moving your W. Let's say that you are making very small change in W, very small change in W. So your error, let's okay. Let me maximize it. Okay. So now let's say you have taken some initial value of W such that W1 such that the error is here, right? At this point, at this particular point. Now you make a very small change in your W1 and make it to W1 dash. So what will happen? The error will shift very slowly also, right? Your error is also going to shift very, very slowly because you have made a very small change in W1. Or otherwise, let's assume that you might, your W1 originally was here and you made a very big change in W. So your error might be here at this point. New error might be here, or it might also happen that it might come here also, right? It might change that how gradually you're moving your W. So there is this terminology that says that you should very slowly move your W so that you don't miss your minima. Assume again, let's assume that you slowly moved your hair till here. So you have come till here. Your W1 is here now. And now you suddenly increase, you did a change in W1 so large that you came here. You came at this point. Now this is bad because you missed the global minima in here, right? So what people say that you should very slowly move the value of W, very slowly. You should do all the changes very slowly, and your dE by dW, your dE by dW should be controlled by some another external factor, and that factor is called alpha. Now, because if you go down the screen, if you see, I have multiplied this dE by dW term with a thing called alpha. Now this alpha is with you. This is a constant and this is in your hands. You can change it anytime that you want, right? So what you will do is, I'll move back up here. So what you will do is that you will select the value of alpha such that it is moving very slowly, right? But now there's a disadvantage also, because if you move very slowly, then let's say you are here, then you will come here at this point, then here, then here, then here. So you might reach your global minima at a very larger time. It will take a lot of time to you. So you have to take a very critical value of alpha such that it moves very slowly. I mean, not
So,
slowly. Yeah.
are you trying to like tune up your model?
This is not tuning, it is just adjusting the thing that how the model is reacting to the changes that we are doing. So it's like we are controlling our own process of the flow of gradients. And alpha, keeping the value of alpha, yes, you can say this is one of the parameters of hyperparameter tuning. Hyperparameter tuning, HPT. Yes, this is one of the small features that you are tuning. So the value of alpha you should keep is 0.001. But again, if someone says you this, well, like I just said you that you should keep your alpha, no, I'm totally wrong. It depends on your data that how slowly you see that your model is moving. This is just the initial value that you should take. So if you will see all of your major frameworks like Keras or like TensorFlow, you will see that they have put a value of 0.001 also by default. Make sense? Till here, anyone is having any doubt? Let's say that if you want to do it for multiple cells, this is how it looks then. I don't want to scare you, but this is how this mathematics goes backwards, and then you do all the changes slowly. If you want to see the weights adjusted also, I have a picture for that also. Let me. Yes, this is how it looks like. Anyone, any doubts till now? Okay, I have some questions. Cool. No questions? Then I think we should move forward and I should show you some things. Okay, now I will take questions from the previous class that someone asked me that how does the image looks like, and I showed you this GIF, right? So I told you that this image is nothing but images are just numbers. Numbers ranging from 0 till 255, where 255 being the highest value and 0 being the lowest value, and these are called pixel values. These are pixel values, pi values, right? These are pixel values to you. These are pixel values. This is how the images work. But the image that you are seeing on your screen, this is a single channel image, right? This is a single channel image. Now you might have multi-channel image also. Let me show you the demo. Okay. Okay. Last time, anyone in doubts in backpropagation, because this ends your theory for uh, deep for neural networks, right? Neural network intro is done here, right? Feminist was the data set where everything was written, in 1, 2, 3, 4 was written on images, and we need to predict out what is written on the image, right? I told you there are two things now. One is the image, and second is what is actually written on it. That is called labels, right? So we got the data set, and then we started doing it on Keras. But today we will do it on TensorFlow also. Why on TensorFlow? Because I want to give you a basic idea how code in TensorFlow is also written, and how Keras is helping you in how much lowering the works. Otherwise, you won't get to know that how much things Keras is doing in on itself, right? I'll do the first basic. And if you think this is not visible to you, I can switch to this also. NumPy as NP and import. What else can we do? Matplotlib. And guys, I'm requesting you, please. I know many of you are working and you don't get time to do all these things, but please take out time and start doing at least some revision. Okay, I'll do these 3 imports. I'll check the version of TensorFlow, what that we are using. So I'm currently using 1.8.0. If you're using anything else, don't worry. R's code might at some place differ, right? Don't worry, but if your code varies, right? So how do I get the data? I get the data from tensorflow.examples.tutorials.mnist. So actually TensorFlow is already downloaded, not downloaded, but they have put this inside their in their syntax. So if you go inside these tutorials, you will get a lot of I'll show you also. Let me show you how many examples do we have. I have also never seen these, but okay, so currently they have only MNIST here. They're adding slowly other things also. Okay, so we have MNIST here, then we do the input data also. Input data, let's say we do this. Anybody remembers the syntax that is called a read datasets? Read datasets expects from you is that it requests you the input data dot reads is first is the train dir. Where do you want to keep the data, right? You can see all these things written here, right? Train data, fake data is equal to false. Yes, we don't want to fake data. One hot. Everybody remembers one hot encoding, right? That we did last time also. If you have any doubts, please ask. Let me know. The current default D type of the data is float 32. That's good for us. Reshape equal to true. Validation is equal to 5000. That's correct. seed is equal to none, and source URL it is written here. So the URL is actually here from where it is going to download. So you don't have to tell it the download for it, right? We will just say where do we want to keep the data. So I'll keep the data in. I'll keep the data in MNIST underscore data, right? This will create a folder there, MNIST underscore data, and I want the one hot encoding to be on. So sorry guys, I don't have space to write because of this true, right? Okay, so what has happened here is that now by default, if I see and go in my data section here, so I might have a MNIST dataset in my data folder, right? I'll show you. I have a data folder and see here is this MNIST data, and all the four files are here. Which four files? If you remember, we did this also. MNIST, right? These four files that we saw. Yes, that also. If I'm not wrong, we have done this I have shown you this website. I've shown you what data set it is, right? Correct? Correct me if I'm wrong. Okay, so now what we have done is we have downloaded the data and it is in the one hot encoded data set, right? Now I did one mistake here. I should have first of all said import warnings, and warnings dot filter warnings and ignore. Why I am doing this? Because I don't want to see this all warnings here. You can see this is just warning. So I don't want the warning to be displayed every time. Just don't want it. So now you will see no warnings. Correct? Now let's see what is inside MNIST. If we check the type of this, so it says it's a dataset type of a thing. Let's see what things it can help us. Okay, so it has actually three things: test, train, and validation. Let's go inside what is this test train, and you can see that there is dot index and dot count. It means it's actually a tuple. It's actually inherited from a tuple thing, right? Let's go inside train. Train may, if we see, there are images and labels, right? Let's go to images and then let's see what is the first image. First is this image. This image looks like something like this. Let's do one thing. Let's print this. Let's plot this image, right? How do you plot this image? plt.im show, right? But im show will take two things. What? At first you need to make sure that your image is a 2-channel or 3-channel image. But if you see what is the shape of your current image, currently it is 784. 784 is not a valid image, right? A image should have a width and a length, height and width simultaneously, right? So there is no. So what you have to do is that you have to do a reshape of this also. We know 784 is a square of 28 cross 28, and we know these are the images of 28 cross 28. Now you get 28 cross 28. We'll do a 1 also. Why? Because I want to show that this is a 1-channel image. Now if I do a plot, sorry, my mistake. right? What we can do more is that we can make it gray so that you can see the actual color. This is how it looks like, right? So the first image looks like this. This first image looks like this. What I can do is I can print the label also for this corresponding image. What I'll say print MNIST dot train dot label, but I have to make sure that I'm giving it the same number. So if I've given 0, then I'll give 0. Because this is one hot encoded, now the data is in one hot encodation, and you can see 0, 1, 2, 3, 4, 5, 6, 7, right? So you can just say control that. I can make a function out of it, and I can say plot underscore image, and we can accept a number from the let's say we want to print 59900th image. This is actually a 0, 1, 2, 3, 4, 5, right? I'll take a pause here. If you have any questions, queries, please ask.
The above definition, what can you please explain what that is MNIST train dot labels number?
I am sorry. Can you ask again? I'm so sorry.
In the above definition, define
Uh-huh.
plot dot. So in that,
Uh-huh.
what the function
Okay.
does.
So what MNIST is giving you? MNIST is giving you three types of data. If you see here, if you pay a small attention, it says three things: test, train, and validation, right? So now what you did was you went into train and then you said how many things are there? There are actually two things. There is images and there is labels also. So labels and images, imagine there are a very long list, a long array, where for every corresponding image there is a number written there. So what I'm doing is that I'm asking MNIST that inside your train data set, if we have images, give me a image called num. Num is actually a function here, right? So num is actually containing 599. So what is the 599th image? Just try to plot it. Now because if you see the shape of MNIST train images, it is actually 784, 0. Now a image is not actually a 784, 0, right? It is flattened image just to save the data, right? So what we're going to do is that we did a reshape of this image. Because we already know from the Yan LeCun site, if we go to the Yan LeCun site, you can see here that they have clearly written that the image is actually a 28 cross 28 image. Here if you see. If you read this very carefully, it says 28 cross 28, right? So we know that how that number 784 came from. So what we are doing is that we are now converting it into dot reshape 28 cross 28, and then I'm asking, don't print the normal image, just print me the image with the grayscale tag. Any issues? Concerns? Then the number I gave it for image, I'm giving the same number for the label also. Make sense?
Thank you.
Okay. Any other person who has any doubts, concerns? If not, we'll rush further. Right, once we have got all the data, once we have got everything inside us, what we are going to do is now we are going to make TensorFlow variables. So to store all these images, weights and biases, we are going to make placeholders, variables and constants. If you remember these definitions, so what we are going to do, we are first going to make a tf.placeholder. This placeholder will keep all the images, and we'll also have a y that will be that will a y that will contain all the labels, right? For every image there is a label. So what will the model do? Model will try to learn all the features from the image and try to map it to 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So what we're going to do, we are going to say tf dot placeholder. So first is actually the d type. D type is df dot float 32. Correct. Then it asks for the same second thing is that is shape. Shape is equal to none. No. We don't give shape is equal to 28 cross 28. We give it the full image. We are not going to do the unfolding of the image. We'll let it remain flattened only. Right. Now we are going to make the weights. How do we make the weights? Weights is equal to tf dot variable. Right. By default, we are going to initialize them with zeros. Correct. How many zeros? 784, the number of inputs, and the next column output will be 100 only. Right. Can anybody explain me how did I came with this number of weight 784 into 100? Anybody? No, I'll tell you. So see, what is happening here is that we are creating a variable called w. Now what this w is going to correct. So our neural network will look somewhat like this. But sorry, we don't have so many. So let's say this is the input. But we have only 10 outputs. This is the input layer. Input layer has 784 columns that we already know. And I think who answered that correctly? Okay, and this is the output. This is the output, right? So what is happening here is that you have 784 inputs of an image inside your input layer, and then you have 10 outputs. Now, how many weights will be there inside? Let's say that this has to connect to every 10 of the outputs. 3, then 4, then 5, then 6, then 7, then 8, then 9, and then 10. So this is just one input. Then you have 783 other also. So what will be the number? Right?
So
Everybody understands this?
7,840 probability.
That will be 784 into 10. Right? That means number of weights we will have inside our thing. Right? And I did a mistake. Sorry. I should have written it 10. I have written it 100. Sorry. Right? These are number of the weights. And can anybody tell me how many biases will be there? Anybody? How many weights? How many? Sorry. Bias is correct. 10 only. Why 10? See, because you will connect this 784. Let's say these are 784 and these are just 10. Right? 1, 2, 3. Where are the biases connected? On the this end. Okay. Now once you're done with this W
Sorry, Shyam, to interrupt. You said that biases will be connected means this 10 biases into the number of hidden neural
Correct,
neurons, right?
correct. I'll explain you again if this is not okay. Other people also wanted to. I'll tell you. So see, again I'll draw. Let me bring out my. It's not here. I lost it. Okay. So see, what is this? This is your inputs, right? These are your inputs, and let me change my pen. This is your output. Now, how many outputs do you have? Only 10, right? Currently, I am drawing just 5. Now, how are these connected? These are connected somewhat like this. So, weights are connected to every node, right? Everything is connected to everything, right? So, you can, what you can do is how many weights will be there? Input into number of output, right? Input into number of output is equal to the number of weights. But how is the bias connected? A bias is connected somewhat like this. Let me give you an example here. A bias is connected to every output neuron like this: B1, then B2, then B3, B4. Or you just imagine that bias is nothing but bias is actually a input only, but that input value is 1. So let's imagine this is x0 here, and you have input called from x1 till x784, right? These are inputs. Now just imagine one thing, only one thing, that if you have outputs here and these outputs want to connect to this x0, how many lines will you have? If you want to connect this x0 to every output, how many lines will you have?
It will be number of
Outputs,
output
right?
into, yeah.
Number of outputs only, because you're connecting just x0 to outputs, right? So now how many outputs will be there? That will be number of biases, right? So how many outputs do we have?
10.
10. So the bias will be 10.
If we consider only one means direct, in this case we are considering one net only, right? One input
Correct.
layer and output layer.
Correct. So what we are currently doing is we are just making it for one layer, right? So if you are making it for multi-layer, then you have to do it for every layer, from here till here, then for here. So you have to do it for every layer.
Yeah.
Did I make sense?
Yes.
To Omar also? Omar, is this helps you? Concepts of biases? How did biases came up? So bias, imagine bias is nothing but actually an input called x0 whose value is just 1. Cool? Little bit? Still query, please ask. Whatever you have in your mind, just let me know. I have to read a little bit more. Okay. I think I suggested you guys a book called Neural Networks and Deep Learning by Michael Nielsen. That is a very genuine book. Please read that book. That is very helpful. I was reading that bias is threshold value. Threshold value of what? I did not get it. Okay. You are saying that I did not get the book. Okay. I don't understand. You didn't get the book URL or the content, because book is free. I'm again posting the URL here. No, I think I posted the URL here only in the chat only in the last class. This is the book. Do read it. It's pure theory. The people who want to go inside the theory of neural networks and deep learning, they should definitely read this book. There is no escape from this book. Please do read this book. Okay.
Yeah, Shivam.
So what? Yeah. Sorry.
Yeah, actually, the bias is for simplifying the mathematical calculations, right? Am I right?
Correct. Totally correct. So what happens is, if you're going to be in the let's say in a binary classification problem where there's only one thing, that is true or false. At that time we face this issue when we are calculating the cost function. That time we face this issue. That's why we have to introduce this thing called. So just think of bias as a weight only. Just think of.
Here, like in the same book which you mentioned, I was reading that neurons output 0 or 1 is determined by the weighted sum, which is less than or greater than the threshold value, and that threshold value they call it as bias.
Correct. So why they have written this is because, let's say that your bias, that your weightage is going nothing. It's going nowhere, right? Let's say it's a 0. Then who is going to decide your output? So a bias is actually a safe side prediction, where not a prediction but a safe side calculation that we do to avoid things. So whenever you will do a binary classification, you have only one thing, right? Either true or false, right?
Yeah,
At that time, when you will calculate a cost function, you will get an error there. That how will you produce for 0 and how will you produce for 1? That's why we need to introduce this thing called bias instead. So just consider bias as another weight where it is actually connected to an input, where input ka value is equal to 1.
Weight or weighted summation of
No.
input
Weighted.
and
Only
weight.
weight. No, I'm saying just consider, just for simplifying the process, just consider bias as a weight only. And weight of what? Weight of an input called x naught, whose value is equal to 1. So when you so what is actually that we are doing is that we are multiplying every, what are we doing in the affine? Affine mein we are multiplying every input with its weight, right? You remember the affine equation, x1 into w1 that we discussed in last class. So if the value of, we do like this, right? x1 w1. So what is happening is the value of x1 is equal to what? I'm saying keep it 1. Then that becomes a b.
So whatever you're calling that, is this called this perceptron model? Because I was reading perceptron, yeah.
So perceptron model is nothing, but it is the same model that I showed you on the very first day. That was just single neuron, and an affine was happening. Remember, I was just showing you a single neuron. There is only one circle, and an affine is going on, and an activation is going on. That is what represents a single neuron entity of a neural network. Now let's say that we have declared these three things, x, w, and b. These are the three things that we want to declare. We also want to make a y also, correct? See, how I am going to declare y is very important. I will say tf.nn dot softmax. What is softmax? You guys remember? Softmax was an activation function. What was that doing? Can anybody tell me? Okay, how many are able to relate to this thing that I have written?
Shivam,
multiplication.
Okay, and how? Okay, so you are totally correct. And how many of you can relate this thing to? Just a second. Where is our last class? Just give me a second. Last class. Theory to intro to neural network. And how many of you can relate to this thing? How many of you can relate this with this thing? This sentence that I've written here on the top, and this one. You decide. Then till then I have functions. Yes, Khem is totally right. It is called the affine function. And then Sanket is asking, deciding which neuron to turn off and turn on. So sorry.
I was saying that softmax function decides which neuron to be turned off or turned on the basis of weight and biases.
Exactly not exactly, but you are somewhat right, but that is a special case that you're talking, just a special case where you're talking, and that is called a binary classification, where that's just true and false, right? So it has no option. So what it will do, it will go with the maximum probability, and it will say, okay, because the weights are more, you are allowed to go, right? Whereas what is a softmax function? Can anybody tell me the equation of a softmax function? Summation of e to the power minus z above e to the power minus z. So what this actually is doing is, it is taking all the probabilities of all the things, and then it is making sure that the probabilities ka sum is equal to what? 1. So let's say that we are doing a MNIST problem, right? Where what are the different outputs that we can have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we can have 10 outputs, right? So what will the affine do? Affine for every output. If I show you, just give me a second. So whenever your output is there, just imagine these are the 10 outputs, right? And you gave a image of 5, right? What you did, you gave a image of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are 10 outputs, right? And let's say this is the fifth one. Sorry, let's say you gave the fourth image, right? You gave the image called 4, right? You gave this image that was looking like this. Now what is happening? Now the neural network has done all the calculations, and it thinks it's the fourth image, right? So what it will do, it will give probability. It will give probability for every class. It might be high or low, but the model will, at every output, model will give some probability, that this is this probability. I think probability of having a 1 is this, probability of having a 2 is this, 3 is this, 4 is like 98%, right? And it will give probability for all. Now what you will do, you'll pick the maximum one. Now who is giving these probabilities actually? Softmax. Softmax is distributing. So Oman is saying that, oh, so it is just converting data into probability distribution. Yes, totally correct. Totally correct. It is converting the data into data probability prediction. So softmax is converting all the numbers into probability distribution, whereas the sum of all these probabilities, all the probabilities that it is giving you out for all the outputs, the sum of all this should be equal to 100 or 1. I mean, if you're taking in terms of percentage, it should be 100, and if you're taking in terms of probability, it should be 1. Make sense, Sanjay? Omar, making sense to you also, right? Helping out? Cool. So yes, I was asking one thing, that is this photo saying the same thing that I've written in this highlighted cell also? Yes. So we have converted this operation that is showing in this image into this one line, right? Softmax ka code, I mean, you can see the function. The function is if you see the softmax ka function, it's e to the power minus z upon summation of e to the power minus z. If you want, I can send you all the sheets with all these formulas and all, right? So we asked, first we did the affine, we did a matrix multiplication of x and w, then we added bias into it, and then we did a softmax of the whole thing, right? We have done this thing, right? This is the one that we are going to calculate. This is the y that is being calculated, but we already have the y that is with us also, right? That is called y actual. We also have the y actual with us, so we have to create that y actual also. That is called dot placeholder. We'll create a placeholder for that. Placeholder should be of 432, and the shape should be, shape will be, can anybody tell me what will be the shape? That will be 10 only, right? Why it will be 10? Because our image will have only one thing, right? If this is the image, the output will be 4, right? Why I am giving 10 here? Because we did a one hot encoding. You remember on the above we did this one hot encoding here at this point. Now what does one hot encoding does? One hot encoding says that your data is actually not in the form of 1 2 3 4. Now it has converted into zeros and ones, and you can see it here very much correctly at this instance. Whenever you are writing 5, you are writing in this format. Correct. KM is totally correct. It's 2-dimensional. So now what is going to happen, that for every image the answer will be in 10 length, right? That's why I'm giving this, right? Makes sense to everyone? Now what I'm going to do, I'm going to do the cross entropy. What is this cross entropy? I'm telling the neural network that you have to go back and do all these things also. So what I'm doing, I'm saying him to do a reduce mean. I'll tell you what I'm doing, don't worry. Reduce mean of tf dot reduce sum of what? Y minus ya minus tf dot log of y. I've done the sum here, and then reduce mean of this, comma reduction indices is equal to -1. Not -1, it should be 1. I know this is a bit tricky, but can any one of you want to try this thing? What is actually happening here? Okay, I'll tell you. What is happening here is, at this particular step, what we are trying to do, we are trying to calculate the errors for back propagation. What we are going to go, we are trying to calculate the errors. And you remember error was actually what? In the last class we discussed this also. What was error? Error was nothing but y actual minus y predicted, right? This is what I've written here also. This is y actual minus log of y predicted, right? Now what I'm doing, because y actual and y predicted will be, let's say this is the output for all the cells. So it will have some y actual. Let's say it is the image of 4, right? So 4 image pair y actual will be 1 here, right? And other than that it will be 0 0 0 0 1, and then 0 0 0. And let's say it's giving some probability 0 0.01 0 0.02 0 0.1, let's say, and at here it will give 98. So what you have to do, you have to minus all these things, right? And then add up. I'm doing the same. I did a minus ya minus log of tf log y, and then I did a sum of it, right? Reduce sum of it, and I've reduced it to the indexes, first index, right? And then I took out the mean of it, because it is the cross entropy is the mean actually. You divide by the number of observation. That is called the cross entropy. So you have the cross entropy with you now. Everybody gets the idea? I'll take a pause here. Have a look at the screen.
This reduction in this is one, this I couldn't understand.
Okay, so see what is actually happening is that these why we wanted to go with the numpy also, but okay. So imagine you understand these are outputs, right? These are output neurons, right? And let's say the image is of number 4, right? So one hot encoding will say this is y actual. What it will say y actual? It will say y a upon 0 0 0, and it will here say y 1 z1, right? And then 0 0 0 for all. And what will your y predicted say? Y predictive will give values for everything, right? It will give something. Let's say it gives 0 here, then 0.1 here, 0.1 here, then 0.2 here, right? And then let's say it gives here 0.9. Let's say it gives 0.9 here, so it will be 0.02. Let's say it gives here 0.9 and something. So what you have to do is you have to minus these things first. This is what we did also, right? We did a minus here and then we got the answer. Let's say answer is here, and then we get the sum of this. But this is only for one image, right? We want to do it for all the images. So what is happening? I'm saying it to the model that model do it on the first index. Now if you see properly, what is the first index in every shape? None here. And what is this none? This none is the number of images that are going to come inside this. See here, none. Now it's making sense to you? I can tell you again. See, what I'm doing is that I did this sum. You understand the sum?
Yeah, this is fine. Yes.
Yes, you did the sum here, right? But we want the sum to happen over this axis called 1, axis 1. Now, what is on the axis 1?
The axis one. Okay.
Right? What is axis 1 actually? This is called none right now here. If you
None
see
right
on the
now.
axis y, none. And none is what? None is actually the number of images that we are going to supply here. So we want the sum to go across all the images.
Okay.
And then we'll take a mean of it.
Okay.
Is it okay to everyone? Okay. If it is okay. Now what we have to do is that we have to minimize this thing only, right? Cross entropy is actually our error, and we have to actually we have to minimize this. Now how will we minimize this? This is called a training step. Anybody remembers the name of the equation that is used for backpropagation? Anybody? Gradient descent. Remember? So what we're going to ask to gradient descent, we'll say gradient descent, bro. We have this thing called cross entropy. Please reduce this please reduce this so please reduce this cross entropy for us. Minimize what? Cross entropy for us. Correct? Okay to all? Now whatever we are going to do, what happens in TensorFlow? What is the golden rule of TensorFlow? It says that whenever you want to run something, you have to run it inside a session, bro. Ses is equal to, today we are going to use a new kind of a session. Let's say it's interactive session, right? It's actually a session only, but you can handle it very carefully, right? So it's actually made for what you call, for all your Jupyter notebooks only. So you can do a interactive session rather than doing tf.session. You can do interactive session, right? Now what you're going to do first thing when you, sorry.
Yeah, what is the difference between the session and the interactive session?
See, I'll tell you. tf.session is when you are not closing it, right? You have to explicitly close it. But interactive session will make sure that once the process is done, it will close it itself. And interactive session should be used only in Jupyter notebooks only.
Okay.
It is meant for that only. right?
Okay.
Once you make the session, what is the first thing that you always do? You will always remember global variable initialization. There are three things: placeholders, variables, and constant. You can run placeholders and constant directly inside a session, but if you want to run any variable inside your session, then what you have to do? You have to initialize them first. Remember? I'll do the same. I'll run it. Now all your variables are declared inside the session and they are ready, right? Now, but this doesn't do. What I'm going to do, I'm going to start a batch of I'm going to start a range of 500, let's say. At first, let me make it 50 only. So I will run a 50 steps, 50 forward and 50 backward steps for our training, right? And I will say back. So what I'm doing, I'm asking the data to be given in batches. And how will I get it? I will say mnist dot train dot next batch. It will automatically give me batches inside it, right? Then I have to increase this also, because how many training samples do we have? Let me check, just 1 second. mnist dot train dot images dot shape, we have 55,000, right? So I have to make it 550. Did you get the calculation what I'm doing actually here? So what I'm asking MNist is that MNist, please don't give me all the images at once. Give me 100 images, and that I will take it in every step, right? And if I am going to take 100 images, then how many times do I have to run the loop? 550 times, because I have 55,000 images, right? Making sense to everyone, right? Because we have 55,000 images and I'm taking only 100 images at a time. So I have to take 550 times I have to run this thing to complete all the images, right? So what is happening now? It will give me batch X and batch Y. Batch X will contain all the images and batch Y will contain the correspondingly labels of the thing, right? I'll do nothing. I'll just say sess.run and I will run the train step, nothing. And I will do a feed dict. Now I have to feed the dictionary also, right? Because I have taken two placeholders. One is this YA and another one is this X, right? So I have to feed these X and Y also. I know the X is nothing but X is what? Batch X. BATCH, batch X. And I know my Y underscore actual is what? Batch, BATCH, sorry. Batch Y, right? Now if I run this, it will run the session for me. Enter. So now what is happening is the session is going to ask what is train step. So train step will say that you have to do a gradient descent optimization minimization for cross entropy. It is going to ask who is cross entropy. Cross entropy will say that I'm a reduced mean of a reduced sum of YA and Y. So it will go back and it will ask, okay, YA, you are a placeholder, I get it, but who is Y actually? So he'll say, okay, Y is actually a calculation of X, W and B. It will ask what is X. X is again a placeholder. You get the value from your feed dict. But who are W and B? It will say W and B are here. Everybody gets the idea how a session things work in TensorFlow. Please ask your questions right now, otherwise it will become a little messy afterwards. And again, to all who are not getting this also, don't worry. Kiras is much. Yeah, sorry.
Yeah, hello, Shivam, Sanket here.
Yep.
Actually, I want to know means how we decide the batches. Means taking a huge number means in some image processing examples we have to reduce the size of the image And after that we have to train the neural net, right? So
Correct.
the size of the image and the number of batches we train, it
Correct.
affects the means what we can say time of that
Correct.
means processing
Correct.
speed also. So how
Correct.
we
Correct. Totally
decide
correct.
this range this batch?
Very good question. Very, very, very good question. Now I'll tell you answers slowly one by one, right? So first of all, why do we take batches? Okay. The concept of batches came because we don't have as much as RAM we can afford, right? Because we have a limited RAM resource, right? Let's say we have 1 million images. Now, can you just put 1 million images in the forward and neural network? No, never. You have to give them like 1,000, 10,000 images one at a time, right? Because our RAMs are limited, right? We still don't have processing power that can take all the images. Now your question comes, how do we decide this batch number, right? Let's say that we take a very large batch number, right? So what is happening, that all the images are going try to go inside the network, but again what will happen, that because all the images are going together, it will go fast. Definitely it will go fast, but again the RAM will exhaust at one limit, right? Let's say that we reduce the image only to one image at a time. Now give me now I'll ask you this one simple question. Okay, you decide and tell me. So let's say that I ask you to classify let's say two animals, and you have never seen those animals, right? These are some African animals that you have never seen, right? And I am showing you only one image, and I say let's say the animals name are animal A and animal B, right? And let's say I only give you one image at a time, right? And then I say you that, Sanket, this is animal A. Now and the next time I show you the image, I ask you that what is the probability of animal B. You will say to me that, bro, I have never seen animal B, right?
Yes.
Right? You will say this to me, right? That's why we cannot minimize the number of batches also. So we have to make a certain ratio of the batch number such that the model is also getting generalizedly trained. Are you getting my point? What I'm trying to say? This is pure theory. That if you're giving a very less number of batches, then it's difficult for the model to run. But if you are giving a very large number, then you're forcing the model to learn multiple features in just one go, right? That's why you have to decide this number very precisely based on how many features in your images do you have, how difficult your images to categorize, or let's say that if you're training on two images, that what is the difference? Is the difference very significant? It can be caught very easily, or is it very difficult to catch, right? That's how you define this batch number.
Sorry, one more I just wanted here is we have to choose precisely, but how can one choose if he knows the parameters, if he knows the number of images and the number of features which on which he is differentiating the image, right? How can one decide on considering these parameters?
I
How can
totally
one decide?
understand. Correct.
Means
I
you say
totally understand
precisely.
your question.
Actually,
I had the same. Yeah. Please go on.
I have ran some image what I can say classification problems.
Models.
But at the time, I was not
You
sure
have no
how.
idea.
Yeah.
What batch
So I
number you
was
should take.
trial and error. I was doing trial and error. Which batch, how much batch, and the resizing of the image was also a little bit tricky one.
So okay.
I mean,
Yeah. I have to answer one more of your question. That how do you do? So Khem is writing correct. That more data, more model, more effective. Yes, that is true. That is certainly true. But okay, Sanket, to your answer is, first of all, let's say that you're talking about this thing again and again. That what is this resizing thing? So see, why majorly do we resizing is because, see, if you're giving a HD image to a model, it doesn't make sense to it, right?
yeah, actually, I'm not saying about resizing. Resizing also is also one of the factor, because if I resize the image to a very small size, means suppose a 1000 by 1000 pixel image, if I reduce it by to 20 by 20 pixel image, then the processing speed for that entire data will be fast enough, right? but it will minimize the features in that. So if I reduce to that to some 500 pixel to 500 pixel, then the it will take some more processing time. But when I take 20 by 20 image size, then I can give a large number of what I can say batch size. But if
Batch
I
size. Correct.
yeah,
I get the idea.
but
What you are trying to say. So just to RAM to accommodate. So this is a very good mathematical calculation that you are doing. That if you reduce the resize the image to a smaller content, then you can give a very large batch number. But you have a very high definition image, then you have to make sure that your batch size is very limited. But you have to make sure, Sanket, here that you have to see that you should not even reduce your image to a very small extent that even model cannot take out. So because if you go and see the algorithm, that how does the cv2 dot resize work, or how does the image resizing algorithm work, the features are somewhat lost. But you have to now make sure that at which extent do you want to resize your image, right? Second is,
yeah, absolutely true.
so see, why I'm saying this is because, see, at the end of the day, when you are resizing your image, so the next time when you're doing the prediction from this model also, that time also you have to reduce this image size.
Yes.
So I'll say it again. So if, let's say that you reduce the 1000 cross 1000 image into 200 cross 200 image, and then you made your
Hmm.
model. Now what you have to do is, then while you are predicting the images, at that time also you have to make sure that your images are reduced to 200, and then only you can do the prediction also.
Yes. So, is there any some mathematical formula or means some kind of calculation? So, can one decide to means approximate batch size or like that?
So okay, yeah, correct. So see, I'll tell you. First is that it totally depends on the data that you are working. So I'll tell you two different use cases. One is that you're working on this thing called on a classification of nut and bolts. So nuts are cylindrical in size, and bolts are hexagonal in shape, right? This is one thing that you are doing. And second is that you are working on the very minute wiring classification. So you have a model of
Hmm.
multiple wires going inside. So have you seen that image, that when multiple LAN wires are going inside server farms, right? That image
Yeah,
is given to you,
you can
right?
say of PCB, a
Correct. Or
PCB.
PCB
Yeah.
also. Correct. PCB motherboard connection you can also take, right? So now you're
Yeah.
working on this minute thing, right? So now
Hmm.
you have to make sure that how is the model going to differentiate, right? So it depends on the data, right? So if bolt and nuts are there, they're quite differentiable at the very first instance, right? And if you're
Yeah.
working on wires, they're very minute, and it's even difficult for humans to differentiate. And how can the model differentiate, right? So the first thing is data. That your data is the first thing on which you can decide this number. Second is that people have made generic models like VGGNet, ResNet, and ImageNet. So what I generally do is that I take inspiration from these papers, from these models, right? So because you see, we don't have much time to experiment with this, because our client is standing there, right? Second, this is the second thing, right? So what I do is I take inspiration from other models, right? Third is that I do this elbow thing, elbow algorithm. What does elbow algorithm says? It says that if you it is a generic equation for every brute force thing. So what you do is you draw a graph here. On the y-axis you have the error of your model, right? And on the x-axis you have the batch size. So what you do,
Hmm.
you start your batch size with, let's say, 1, and you go with 10, 20, I mean 50, first 10, and then 50, 100, 200, and then you go with the maximum amount also, right? Then you
Yeah.
will see a graph somewhat like this at this section. It is almost like a elbow, our hand elbow, somewhat like that. And this is your optimized batch size that you should take. This is the optimized batch size that you should always take. So first thing is your data. Your data will tell you that how much you have to resize it. So I'll tell you how do I decide this. That I told you that I take inspiration from other models. So I have seen that VGG works on the 2 to 4 dimension. So they resize the image to 2 to cross 2 to 4 cross 2 to 4. So what you can do is that you can resize your image to 2 to 4. And I have seen bigger models, like the new model that I was working yesterday. It took an image of 500. So I have never seen a model with more than 500 cross 500 image. But again,
Okay.
it depends on your data. Again, it depends on the data.
Right.
Right?
Mhm.
See, batch size is just one number, right? Now you have to decide multiple things. First
Yeah.
is batch size, then how many layers, and then in one layer how many neurons. So there are multiple hit and trial that you'll do. And believe me, I asked the same question almost 5 years ago to my mentor also this, and he was also giving me something that you will decide with this experience. And the more models you will make now, you'll get the more ideas.
Okay.
Slowly, whenever you will be dealing with data, you'll get the idea. Okay, this is quite difficult. Difficult for the model to train. So I have to leave the leave the model to a very specific area. So you'll reduce it to very specific area, and you'll crop it in a very good manner, right? And then you will give a generalized batch size, right? So right now what here we are doing is that we are giving it a random batch size, right? So model on itself is taking random images from itself, right, from the data pool. But sometimes, let's say that I'll tell you, I was working on this example of watermark detection. So what I was doing, I had to build a classifier model, whether there is a watermark present or not. Okay, so now tell me, how will you do this problem? Any ideas?
Watermark means visible watermark, you are saying?
Yeah, so watermarks we see on the images, right? So there is this problem. So let's imagine that you are a real estate client, right? Let's say you are housing.com, right? And now people are uploading photos on magicbrick.com also, right? So what they're doing is that they're uploading images from magicbrick.com to your portal also, housing.com also. And this is a violation of rules, right? Because magicbrick.com has its own priority images, right? They have their watermark on those images. But now people, what agents are doing to save time, they are uploading the same magicbrick images to your portal also. And now magicbrick will sue you. Why? Because you are using his images, their
Mhm.
watermarked images. So you have to restrain the users from using those images. How will do it?
First, I have to identify is there any watermark of
Correct.
Magic
So
Brick
you have to build
on there?
a classifier for this only. That you have to tell that this does this image contain a watermark, yes or no.
Right.
So see, this is a very I worked on this problem almost 2 years back. So what was this problem? This had the same problem. So imagine this is a image, right? And similar to this image, same copy of this image but with a watermark at a very small level. Now watermarks, you know that watermark are not colored in nature. They are transparent
Yeah.
in nature, right? And they work on the alpha channel. So what is this? That
Correct.
they don't even have some color on them also. So what you can do, you cannot even convert your image into a single channel image also, right? So you are asking this question, what is the resize? I'll give you one more problem. Other than resize, you have one more problem. Rather than converting your problem into a single channel image, you have to keep it now into 4 channel image, right? And if I reduce this image size, what was happening? The logo was the watermark was getting squeezed out, so I could not resize the image also. So that's why
Okay.
I had to take a model with the constant image also. So it depends on the problem on which we are working, right? Second, I'll tell you, I was working on this PCB wiring also. I was working here, and this was not actually a PC wiring, it was actually a car wiring system, right? So there was this engine was also in the photo, there was multiple things inside the photo, and there it has a very small slot in which images were going inside, right? Now if you give the model this whole engine and all these things, all those noise also, the model is not going to understand anything. So what I had to do, I had to crop this section first of all. This small section, I had to crop this small section, and then I had to give it to model. and then only I could do it, right?
Yeah. Yeah.
So so your question is totally valid, and I can totally relate to it. I had the same questions. I did the same questions, and I also could not get this. But believe me, slowly. Yeah, interesting news. Yes, bro. So you'll get interesting problems in AI, and the best part about AI is that what is happening now. We are out of the bubble phase right now, so everybody understands. Okay, things work on their ways, right? But still, people, they have very interesting use cases, and they ask you that, can you do this with the um, AI? Can you solve this with AI, or can you solve with this section? And imagine, believe me, you'll come out with some other way. You will come out some other way that you guess you can do this and that and all, and you'll come with it. Don't worry at all. Yep. Sanket, I know I couldn't give you a correct answer, but did I make sense to you? Because see, you can
Yeah.
read multiple blogs. I mean, you'll read multiple blogs and multiple books. You will not get a correct answer anywhere. Even if someone is
Yeah.
giving you an answer, even if someone
I've
is giving you answer, he is giving you for a particular problem. He is giving that. Okay, let's say he's saying, take you take the resize as 300 cross 300, but he is giving it for his particular problem, right? So that's why there's this
yeah.
thing. So that's why what
Yeah.
I do is, if you want to generalize something, go with these models like VGG. What is VGG?
We,
VGG is actually a model that is made by Oxford University on ImageNet.
yeah, I've gone through some blogs also
So
and
what I
some
take is, I generally
uh
take help from these things, and then I work on it. And you should definitely follow this guy, Pi Image Search. He's a very good guy. And if you're especially interested in images, you should definitely um, this blog is your savior.
yeah, it's of
So
Adrian
these are the models.
Rosberg.
See,
Yeah.
VGG, yeah, Adrian Rodriguez. So VGG, ResNet, Inception. So you should definitely go with these things, because they are trained. They are trained to be very generic in nature. So they have almost 1,000 categories to classify, and they are trained on 1 million images. So you should definitely take inspiration from these things. I generally take the inspiration from these things, because these are made by one of the greatest people in deep learning and AI section. And second part is that they are very generic in nature. So I take inspiration from them. Correct. Now, once what we have done here until this 33 step is that we have taken a batch of 100 images, and we have trained the model. Now let's see that how do we get let's say ACC is equal to TF dot equals, what is TF dot argmax? Argmax what of what? So let's say YA comma 1 comma TF dot argmax of Y comma Y comma 1. So ACC will come out to be ACC will come out to be what? Where is the ACC correct predictions? ACC dot run. So why is this not eligible to us? Just a second. Okay, sorry, I have to cast it also. Sorry, my mistake. I should say this as tf dot reduce mean, tf dot reduce mean of tf dot cast, ACC with a correction of tf dot float 32. Correct. And take it into the ACC. This is not actually ACC, this is actually correct predictions. Sorry for this thing. We have to run sys dot run. If I run ACC, what things I have to give? I have to give a feed dict of what I have given, only YA, right? So y is equal to I have to give mnist. Okay, I have to give x also, sorry. X is equal to mnist dot test dot images, right? And y is equal to mnist dot, why is it not working? Dot labels, right? And did I have removed the section? I have to put a question mark also. Okay. What is this? Says placeholder shape 10 GPU device placeholder 2 data type. This okay. Sorry, see what I did. I was giving test here and I give train here. I have to give test. Okay, again. Sorry for my mistake. So it comes out to be 0.098. Already running good. I mean, it's not good. The probability should be 0.098, but we didn't have done much of the thing. Only it is just one perceptron, and it can give this accuracy right here, right? This is just to show you that how things will work here and how you can do what I was saying. How will you do multiple things out of it, right? What you can do, you can get your, I think, weights also. Simply you have to do sys.run and you have to get out your W here, right? WN, you can get your weights also here. So these are all the weights, and weights should be 784 into 10. These are your weights. You have your weights here. Similarly, you can have your biases also here. Biases you can have .sys.run. Now you can do B. B.n should be equal to 10 only. Yeah, 10 only. You can do C here also. Right? This is just to give you an intuition that how will you do a change. Sys dot close. Very important. Just do this. CNNs. Now CNNs are actually a new kind of not a new, but they are one of the most fascinating kind of architecture that you will ever learn in deep learning, especially in images. So till now what we have done is we have just seen that okay, we are connecting some neurons to other neurons and other neurons to other neurons, and this is something the information is getting passed. And if you remember the maths behind this, that we are just doing a affine, then we do some activation function. It means that we are bringing some non-linearity in the data, and then we are passing it through some activation function, and then we are finally giving it to the next layer. And then this chain is going on. Things are coming in, going out, coming in, going out, coming in, going out, right? But how is this network helping the model to learn the key features, right? We learn this new and very interesting uh, 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 neural network architecture that is called CNN, or commonly known as the convolution neural network. So convolution neural network, what will do is it is somewhat like how do you say? Let's say if this is the original image, then to find out the features inside it, what you are going to do is you are going to take a smaller cube or square. Sorry, not cube. You will take a small green square, and then you'll apply this. You'll put this green here on the top, so it will somewhat cover like this, right? Then you will move this green spot to your right, right? Then one step down, So it will come like this. Again right, then one step down, then again right, then one step down, again right, and then one step down. Eventually this small image, or what we call it as filter, will like run over this whole image, and it will learn the important features and the aspects of the image. Right, now how does this done? I'll show you a very intuitive example here. Wait for a second. I have this wonderful thing running for us, and this is called CNN. Yes, CNN. Let me make a new Jupyter notebook. See, this is somewhat what is happening inside your. So this green image that you are seeing right now, this is the big image, and the orange image that is moving is called a filter. So what you are doing is you are moving the filter on the image one by one. You are moving the filter by one. Now, when I say when you are moving this filter on the original image, what I mean is that you are doing a element-wise multiplication on this image, and then you are summing up all the things. So if I stop this thing here, okay, it doesn't stop. If I put it here, how do you stop this? Yeah, I learned this art. Cool. I got this thing here. Okay, just a second. Just give me a second. Cool. I have this picture already with me. Control C. Okay, so img src equal to. Okay, see this image right now. Right, you can see this image right now in front of your screens. Okay, I'll push it here. Okay, so this green thing, this green image, and whatever this big thing is written here, these big numbers 1 1 0 1 1 1 0 0 1 1 1 0 0 1 1 1, all these big numbers are what? These are, let's say, the pixel coordinates of the big image or the original image, right? And then imagine this orange filter, where small red color me you can see these things, these numbers 1 0 0 1 0 1 0 and 1 0 0 1 1 0 1. These small numbers are the filter. These are the numbers for the filter that is going to move over the image, right? Now when this thing is moving over this thing, it is doing a element wise, or you can say a scalar multiplication. Element wise one by one multiplication means that this one is multiplied by one called 1. 1 multiplied by 0 is 0. 1 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 1. Then 1 plus 0 is 0. 0 plus 1, 0 plus 1, and then 1 is to 1. Right? And then you have one more. So all these numbers, first for this one, second for this one, third for this one, and fourth for this one. Sorry, this one. So these four, this number becomes 4, and you write here 4. Similarly, what you will do is you will shift the now this filter to a little bit of your right. Then you'll have the second one. If you move it to a little low, then it becomes your, see, low and down, it becomes 2 3 4, then 4 2 3 4. This is how your convoluted features are calculated. Everybody gets the idea? So now do you get the idea how this thing is coming? If you see this GIF a little more, once take your time, imagine how this thing is working. It goes on the right hand side one by one. One is shifting, goes down, again one shifting, goes down. And this is how your final image is made. This pink image is your final image that is made. Again, I'll ask you, please take a small time to digest this thing. This is a little uh, not tricky to understand, but a little one should pay more attention to this, how this thing is working and how is the thing going on. Because now I'll tell you what is happening when you are doing this thing. So what is happening is right now here is that okay, just tell me this thing, that let's say if you are standing in front of something, right? And then, so how do you identify, how are your images identifying you as a body? I'll tell you. So there are pixel value that are changing at the border of your body, right? So let's say that you took let's say you're standing in front of a white wall, a pure white wall, and then you're standing. How are you differentiated from a wall? Because if you see, if you open up the matrix of that image, if you open up the numpy array of the image, you'll see that your body will contain a higher pixel values and the white wall will contain 0 pixel values, right? Now whenever your body to wall is there, whenever the boundary of your body is there, right, at that particular instance your pixel values will be changing, right? Because your pixel value would be somewhat like 230, 235, and then suddenly the image of white will be 0, right? So whenever you will be running this filter over your image and then doing this multiplication, what will happen that it will largen up the broaden up the areas. It will broaden up those border areas for you. I know it's not easy to understand, but don't worry, I'll show you things. I am putting his blog in your chat also so that you can open up anytime and then see. But this is his blog actually. So if you come down here, what is happening here is this is what the image looks like, right? We have already discussed this thing that 255 is sheer black and white is almost like 0, right? Now what is happening is, let's say this green was your image, this green thing was your image, and this orange one was your matrix, right? For your filter, right? What you're going to do is you're going to put this 3x3 image over this 5x5 image and then do a multiplication, right? Multiplication say you will be getting a convoluted feature. Right now, if you understand this thing, okay. So first of all, you know this thing is called a filter. Sometimes we call it as a kernel also. This orange thing as a kernel or a filter also. Now see, imagine what you're doing is that you are, let's say this image was not made up of 0 and 1 only, but it was made up of 0 to 255. Now what would be happening is that the larger values, the values that are two. So imagine there are two numbers in front of you. One is called, let's say, 5 and another one is 230. Now if you multiply both the numbers with, let's say, 10, which one will become more larger? There are two numbers, 5 and another one is 230. 230 is the person you who are standing. This is your body pixel, right? But the white background will contain values from 0 to like 10 only, right? Because this is the white wall, a pure white wall. So let's say even if we say that there are some tints and something, so the color density will be, or color pixel, let's say it's 5. And let's say you're multiplying the same with 10. So your 5 into 10 will be 50, but your 230 when multiplied by 10 will be 230, 2300. So what is going to happen is that we are going to do a matrix multiplication, and then sum up all the things, and these are gathered here, right? All the things are gathered here in this area. Now you might say that what has happened if you have gathered larger values, and then there might be some lower values also, because if you are running this thing on a white border also, let's say if everything is 5 multiplied by 10, everything is 50, right? Doesn't make sense. 50 ko you add up all, it will become the same value, right? Now I'll tell you how things change here. When you run this, let's say this was your original image. This deer was your original image. If I zoom in a little bit to show you, this was the image. If you see clearly on my screen, this was the, let's say, image, right? And when you do a filter of this identity filter, it will return you something like this. If you return this filter, it will return you something like this. If you return edge filter, this is something like this. If you return -1, -1, -1, this is called blur, sharpen blur, edge blur. Then you have box blur, Gaussian blur. So this will happen if you multiply your image with this filter and you run this filter on your image with stride equal to 1. So your original image from here, this thing, this particular thing, this thing will change to these things, depending on which filter, through which filter you are multiplying it. Make sense? Now let's say if you're analyzing this thing, this image, what has happened here is that you can easily see that the animal's border are now created or sharpened here, right? You can more easily visualize the borders of the animal, right? Rather than with this original image at here, where the borders were not much they were not much in the same group. Now you can easily do a spread out with just one convolution, and this is just one. We'll like replicate it like multiple times to get more value out of it. Make sense? Now you understand why we are doing this, running a filter over the image. Now this depends that what are the values that you are using inside your filter. Your filter might do a blur of the image also, and it might do a sharpening of your image also. And this edge detection is the something that we want to do right now, that we are very much interested to know that what is the edge of that animal, so that we can differentiate if it's a cat or a dog, right? And this is the perfect example how things are working for us. Correct? Everybody gets the idea? Cool. Now once you have done this filter and you have got a very edgy image, now what you want to do is, still on this edgy image, you want to capture the maximum values. So now imagine that what you have done is you have multiplied a larger number with a more larger number, right? So your smaller number will become smaller and the larger number will become more larger. And then also you are saying that you want to have the maximum values only. This step is called as the second step in our CNN network, and this is called max pooling. This is called as max pooling. The first thing was running a filter over your images, right? That you have already run successfully and you got everything out of your image. Next, what you're going to do is you're going to do this thing. Okay, again, sorry, one more thing to show you. Let's see, with different filters, you have different feature maps available to you. Let me zoom in so that you can see it more efficiently. Can you see it now? So what we are doing is we are trying to run a filter over this, and through different filters, you can see different images are coming out. Different outputs are coming out, right? Make sense? Cool. So what we are going to do is next, what we are okay. Now in this, one more thing I want to tell you is that you should have asked me this question, that in this particular GIF that we are seeing here, we are moving the orange we are moving the orange filter with one step only. Like see, one step it's going ahead, right? You might argue this to me that okay, this is also arbitrary, right? We can move it to 2 steps also. And my answer would be yes. You can move it 2 steps, you can move it 3 steps, and if it's a very large image, you can move it like more steps, right? So it depends on the architecture of your image and the architecture of the filter that you are choosing, right? Now, when I say how many steps do you want to move, this is called a strides. What it is called? It is called strides. So in our case, right now, the GIF that you're seeing, the stride is equal to 1. When I say stride is equal to 1, it means that you will be moving your image, the kernel with one step ahead. From left to right, your kernel will be moving one step. And similarly for going down also. So it's if you see, if you quietly observe that your kernel is shifting downwards with just one row only. It might have shifted to 2 rows also, right? But because you have set as strides as 1 comma 1, 1 comma 1 means that you will be shifting column to 1 and to row also you will be shifting 1. Make sense to everyone? So till now what we have done is we have taken some arbitrary metrics called as the kernel metrics, right? Then we took some arbitrary values inside it also, some random values. Then we have taken this thing called strides. We have by default we are giving it at 1 comma 1. It means one row to the left and sorry right and one to the down, right? So we're cherishing all these things as of now. And then we have got out something that is called convoluted feature, right? Now one thing is for sure that your output is going to shrink from the original image, right? So originally, if you see in your example, your image was around 5 cross 5, and now it has come into just 3 cross 3, right? Let's move to the next stage where we have done this convolution. Now our next step would be to get more more edgy features out of it. So what we're going to do is after we have got this feature map here on the once we have got this feature map on the left hand side, what we're trying to do is we'll again find out more maximum numbers out of it. So what I'll do somewhat like this. Let me show you where it is. This thing. So let's say on the left hand side that you're seeing is the convoluted filter. I mean, this is the thing that they have returned you after you have done your feature mapping, right? Or your mapping is done. You ran the filter over your image and this is done. And this is the output that you see on the left hand side. Now again, what you will do is you will say that I will take a 2 by 2 square, right? I will take a 2 by 2 square and I'll pick up the maximum values that are present inside the image. So what is going to happen is currently your answer is in the shape of 4 cross 4, right? And then 4 cross 4, and let's say that you are making a 2 cross 2 circle, and then you have to find the maximum value. So in the first 2 cross 2 you find 6, in the 7 you have 8, in the third you have 3, and in the fourth you have 4. Make sense? Even this max pooling thing has this size that is called 2, that you can see right now it's 2 cross 2, and it has strides equal to 2. Why? Because you don't want to get the maximum number again and again. So let's say if you're taking this, once you have taken these values, you should move to the next thing, right? So let's say this was your first filter of 2 cross 2, and now you have strides of 2. It means it will shift to 2 rows and 2 columns. So this will be your next row column. Next question will be who's the maximum? You will say 8. So you can see all the values are transferred from 6, then 8, then 3, and then 4. Everybody gets the idea? So see, the max pool thing is nothing but let's say if we go up again till here where you just got this new answer from your after you have run your filter over your image, this is called convoluted feature, right? Now this convoluted feature is actually nothing but an edgy photograph of your original photo, right? So it contains more edges, more clear edges, and more things, but they're still not much clear to you, right? So then what do you want to say to the model is that model, give me more heavier amount of images, give me the maximum number of pixels in a particular area. So you say okay. So what you're going to do is the final thing that you have here right now in the pink 434 243 234. This thing is called a convoluted feature. Now you'll go down. Now once you have got this image, your second step is to take the image and run again a 2x2 filter over it, right? And then with the strides of 2, it means the next step is not one step but two steps, right? So your first square will be 1156, right? This one, right? This one is the first square. How much is your total maximum number in this? 1156 is 6, right? So you give 6 here. Then your second, because it's the stride is 2, so your next square will become somewhat like this 2 4 7 8, right? Maximum thing is 8. 8 will come here. You have next thing as 3 2 2 1 2. Then your 3 is equal to 1. Sorry, 3 is not equal to 1, but 3 comes here, right? Then your fourth square, then this is a fourth square 1034, which is the maximum value 4. 4 is shifted here. Do you get the idea?
What I can understand is the matrix from the earlier picture we are coming to 3 by 3 and then we are again going to 2 by 2 matrix.
Correct. So we are reducing the size of the image just to get the most important features out of the image. So let's say in our example we had a 5x5 image. First we came down to 4x4 and now we have come down to 3x3 and then 2x2, right? So we are reducing all the noises from the data and we are picking up only those things which will be ultimately used for classification, right?
Hello, Shiva. Yeah, what about the information lost over here? Means, as we are choosing the maximum value, the convolution values of other pixels, we are losing this information, right?
Very good question. Very good question. So see,
What
this is
about this?
called pooling. Yeah, correct. I'll answer. I'll try to answer this question. So see, this step is called pooling step. Now, pooling steps are of multiple different types. So here we are interested in more in getting the curves or the edges of the object, right? So we want to get the shape of the accurate shape of the cat that is sitting there, right? We want to get the features deep inside it. So what we're trying to do is we are not wanting to get what is inside the cat, but how is the cat different from the background of inside the picture, right? Because we are not interested in the background, we are interested in the cat only. That's why we are picking up the maximum values that will be differentiating as a border image, right? And I'll show you this thing also. And you are very much right that sometimes you don't need the maximum value. So that's why this is the most used pooling, that is called the max pooling that we are doing, that we are trying to have the maximum value. But you can have three different types of pooling right now. One is called max pooling, then next one is called average pooling, third one is called sum pooling. Now, what is sum pooling is, rather than taking up the maximum value, you do the sum of this particular thing. So 5 plus 6 plus 1 plus 1 is almost like equal to 13. So you give 13 here. Then you have 7 plus 8 plus 2 plus 4, that's equal to 14, 15, 16, 17, 18, 19, 20, 21. You keep it here. And then similarly for all the things, you can do a sum. Sometimes people do an average also, but the most prominent result giving is the max one. And you can imagine yourself also. If you close your eyes, just see this, how is this image transformed, you'll get out the whole idea, right? So if you see this image, let's say this was the image of the building, right? If you closely see that, what was the output of when you run this convolution, that you get all the edges of the building, right? The edges of the building are now more prominent to you. Now imagine that you are taking the maximum values out of it, so it becomes, you are losing all the white information, you have just the black information, right?
Yes.
So see, now let's now again wrap up all these things, and these are the two main examples that you should understand at the first stage. One is the convolution. Convolution means that you're running some random value of filter over your original image, doing element multiplication, and then adding those things, and then having a convoluted filter. And over that convoluted filter, you should have run a pooling kind of object. So you can have a max pooling where you're picking up the maximum values. You can have an average pooling where you're doing the pooling where you're doing the average of the particular pool, or you can have the sum pooling where you're trying to do the sum of that pooling thing. Right. But now between these are the two major steps in convolution CNN terminology, right? But in between these two steps, there is a lot of thing that happens. Right. So let's zoom out of this, and then let's try to cover them one by one what we have missed till now. So see, whenever you're running this thing that you're seeing on your screen, this filter, whenever you're running, you will never run a single filter on your image. This is what CNN is. You will run multiple filters with multiple different values, and that thing is known as the depth of the CNN. So whenever you will say that from keras.layers import CNN, right, or conv2d. So actually the name in the Keras library for this particular layer is called conv2d. CONV for convolution, CONV and then 2D. So it means that you are using convolution neural network for 2D images, right? So what you will do is, at that instance, it will ask you that how many filters do you want to run on your image? How many random filters do you want to run? That is called the depth of the filter, right? Now imagine this photo here that you're seeing here this is a image of a boat that is standing somewhere near the deck, and you can see water and some grass. Now what it is that right now you have a depth of 3. It means 3 different filters will run on this image, and they will produce 3 different convoluted images. Did I make sense here? Imagine that this thing is called as the depth of the convolution. Now depth of the convolution means that right now till this before this example, we were running only one convolution, right? We were running only one filter over the image, and we were getting only one output of that image, right? Now what the model is saying that we will not run one, but we will run multiple. So in this example that you're seeing in front of your images, right, in your screens right now, where this you have a boat inside, where you have a boat near the surface of the earth, you are running 3 different filters, and for running 3 different filters, you will get 3 different convoluted features, right? So you cannot control the value that what is going inside what is the value of those filters, but yes, you have to definitely tell the model that I want to take these many number of filters, because this will increase the depth of your model, right? So you will say, let's say I want to take 25 different depth of the model, or I want to take 1000 depth, for the first image. I want to have 1000 different convolution filters, because eventually their size is decreasing. If you see closely, if you remember the GIF, the height and width of the image is going to decrease, right? But 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 the depth is going to increase. So earlier, let's say if the image was of 1D, with one channel, now it is going to convert it into 3-channel image, because you have run three filters on it. Let's say you ran 500 filters. So for one image, you will have 500 different outputs, right? So see, why we are increasing the depth is because, see, ultimately the model needs to get some or the other final decision thing. See, ultimately the decision is taken by the last layer, right? And you remember that you have to ultimately mold your model to take to the dense layer. And you remember the dense layer are nothing but a single column rows, right? So when I say dense 1024, it means that this is a one column, but 1024 different 1024 different rows are there standing. So you can imagine 1024 blocks are one over the above, right? So you have to somehow converge your model to have, so you're converging your 2D image, which has height and depth, and you want to convert it into a depth only thing, right? So let's say that your image was somewhat here like 50 cross 50 image. So what you're eventually doing is whenever you run a convolution filter, you're reducing its size to let's say 35 cross 35. But when that image is converted into 35 cross 35, you're increasing the depth of it because you're not running single convolution filter because you're running let's say 10. So if the original size was 50 cross 50, now it was converted into 35 into 35 into 10, right? When you will run more, it will convert it into let's say 15 into 15 into 100, right? And then eventually you will be having only 1 cross 1 cross 100. What is
Shivam,
happening is rather than running one convolution filter and having only one answer to the model, what we are doing is we are running 10 and hundreds of filters so that eventually we are like in the end we are clubbing them all so that we can. So if you have done ML, you must have heard of this thing called ensembling of all the models, right? So let's say that you don't want to trust only one model, but you build three different models and then you club all these models. This is what is happening here also. We are not running only one filter, but we are running 100 different filters, and then at the end we are clubbing all their results, right? Let me just scroll it up. So when I say filter or feature, I mean this thing, this small yellow thing that is not known to us. This is the random matrix that we know. So your question, so I totally understand your question. First, to answer the question is that okay, that you are saying right that if you already know that if you can get a edge detection to this -1 -1 -1 8 and -1, then why can't I directly use this, right? But this one is only working on this image, right? Other images might have different convolution because this image was very symmetrically designed. That's why you were able to do this with the -1 and 8 combination, right? But let's say your image is a little tricky one where the polar bear is standing in front of a white image only. So everything is white. At that particular instance, your convolution filter will be something else, right? And now coming to a second question, that are the random convolution that we are choosing, is that correct or not? Who will tell this thing, right? So what will happen is that when you are doing a convolution, you will have some output, then again you do some convolution, then your output, and at the end, the model will try to predict out something, either cat or dog, right? But then your Y actual is standing in front of you also, because in the training data set you give the Y labels also. So your training label is also there. Whenever it will predict out something, let's say it predicts out the probability 0.60 for the cat, but it is actually a cat only. So your model will say, bro, you're doing good. You're doing good that you are saying this is 0.64, but no, you're not saying it totally correct. This is actually 100% cat. So what you do is you go back, right? Go back and increase your probability. Try to increase your probability by 0.4% so that our error is minimized. Currently, we are having an error of 0.4. So go and reduce this error by 0.4. Now the back propagation guy will go and he'll say, okay, wait. Now convolution filter you and you and you three are combining, creating an error for us. So we are changing your results to this level so that you decrease the error. So eventually, whenever you're doing a feed forward and backward propagation, feed forward, backward, feed forward, backward, feed forward, backward, you're ultimately converging your model to minimize the error and maximize your accuracy, right? So at that particular instance, you at the end, when your model is converged to let's say saturated with no more error decreasing or no more accuracy increasing, at that particular instance, whatever convolution values you have, those are the perfect convolutions. And if you run them on your image, you'll see, okay, this is the perfect edgy thing, and then it is trying to classify. Okay, now coming back to the problem where we were, that if you are doing, let's say you have done you have just ran a filter over your image and your image is converted from this simple image to this more enhanced edgy image, right? Now if you go more thing out, so first thing that you were doing was that was called depth. Now, what is depth? Depth means just that if you are running different types of convolution filters on our images, then you'll get different results, right? So if I'm saying I'm running a depth of 64, I mean I have 64 different features which I ran over my image and they gave me the output, right? Second thing is strides. Yes, strides, we already know strides is what? Strides is the step size. That how many jumps do you want your filter to move? So in the GIF, we were seeing that our model was shifting with one space, right? One space to the right, it was shifting. So that time it was stride equal to 1, but if you do stride 2, it means it is going to jump. It is going to take 2 steps, right? Oh, then we have one of the important thing that is called padding. Now you might, if we go up again, if not, let's not go up again, but if you see this thing right here, okay, this is the dynamic one, this is it, right? Let's say if you are here and let's say that this is the first step, right? It has completed. Now let's say that you have a stride of 2. Where will be the next stride position will be? Stride position will be almost somewhat here. This and this, right? So you will have an exact combination of how many. So can any one of you tell me right now that what will be the output shape? So if you are running a 5x5, if you have a 5x5 image, and if you are running a 3x3 filter with a stride 1x1, you have an output of 3x3, right? But now let's say if you have an image of 5x5, you're running a filter of 3x3 with strides of 2x2. What will be the output?
2x2 matrix.
Very good. It will be a 2x2 matrix. Take your time, just do the imagination. Just move the filter in your mind. You'll get all the answers automatically, right? And if you want to create a formula out of it, it will be the original image size minus the convoluted image shape plus the strides. So 5 minus 3 plus 1 is 3. But if you have 5 minus 3 plus 2, it becomes 2. Everybody did the move in their minds? Close your eyes and then if you move this, you'll get the answer as 2x2. I'll do it for you right now. So the original orange one where it is the first one. Then second I have made is the second one. The third one will be somewhere here. Third one will be here. And then the fourth one will be here. And your second one was here. Right. So strides you can. So this is what is called as the strides thing. You already know it. Okay, yeah. So we were talking about sorry. We are talking about the padding part. Okay. Now let's take an example that you again have a 5x5 image, 3x3 filter, but you have a stride of 3x3. What will happen right now? First is here. I can draw it for you. First will be this. The third one will be, the second one will be here. But at this particular instance, you have only 2 columns. Where is this third column? Right? So what you do is you fill it with zeros here. This is called zero padding. When you don't have enough number of columns to fill your things, what you do? You fill it with zeros, zeros, so that now you can have a 3x3 padding. Similarly, if you go down, you will have this problem here also. You won't have an extra row. So what you will do is again you will go this, you'll fill 0 in this, 0, 0 and 0. This thing is called padding. What is called? This is called zero padding. Right. Let's move to the next thing. This is called zero padding, right? Now, once you have done all this, you have run the feature with multiple depth and you have some padding or you have some strides, right? Then you'll get some output out of it, right? Similarly, like you got something here, like 4 3 4 2 4 3 and 2 3 4, right? This pink answer you'll get, right? You'll get an image. Now if I say that please run it through a ReLU. Now if you remember ReLU, what was ReLU? ReLU used to give you the answer as it is if the number is greater than 0, right? But if the number is less than 0, it will convert everything to 0. So what we are trying to say is that if there is a positive number, let it go and fly. We don't care. But if something is negative, we are going to convert it to 0. So what will happen is if you give a image, see if this was your, if you can see clearly, let me zoom in. If you clearly see from here, you can see it right now. If you clearly see from here on the left hand side, this was the output from the feature, one of the output from the feature, and then you ran this ReLU thing. This is what has happened. Only non-negative values are there, all the negative values are gone. You can read there also, it was written black is equal to negative, white is equal to positive values. So all the whites are there, blacks are all gone, right? Now once you have done the you have done the ReLU, then you have this thing called pooling that we were just talking about. Pooling is nothing but it is used for reducing the dimensions but retaining the most important features. And this is what we were talking about, that the pooling can be of different types: max, average, and sum. Read it here, these 3 lines. One of the best, I think this is the articles. He's a friend, that's why I'm bragging this, that this is the best article, but this is one of the best. Right, and especially for new people who just started learning how deep learning, this is one of the best because it is not using any kind of a jargon word. Otherwise people they use like non-spatial locational background of the image will not, and then you won't have any idea what is going on, right? So what is happening is this is a 4x4 image. You take a 2x2 matrix over it. You do a max pooling. 6 is maximum, take 6. 8 is maximum, take 8. Here maximum is 3. Here maximum is 4. Take all these. So what you've done is you take your original picture. You do some feature of you ran some filter. You got the convoluted filter. Then you ran some ReLU, and then on the ReLU you ran a max pooling. So eventually, what will happen? Let's see if you ran the image on a max pooling. This is what will happen. I know this is making no sense to you, not to me also, but somehow this is making sense for the model now. Model is able to understand. Okay, this is dog, this is cat. Now I understand. But if you will see this thing for a very large image, right? You will understand these things also. Let's say if you have an image of 1000 cross 1000 and then you're running this thing, you will definitely capture these things, that what it is doing is ultimately all these buildings are now reduced to a very lower level. This big image has been now reduced to this small image, right? And now if this would have been a high quality image, you could have easily seen that all these tall buildings are now reduced to a smaller level in the things, and we are reducing the dimensionality, right? This is all what we do in convolution. At the end we get this convolution and we get somewhat architecture like this. Now just pay attention for the last moment, right? This extreme left was your original image, right? Then you ran some filters on it. Let's say you ran 3 filters. So the size is 3 filters are here. Now out of one image you can get 3 images, right? 3 different outputs for 3 different filters. Now on these filters you ran a pooling. Now pooling say you reduce the size of your image, right? Again on this answer that you got from the pooling, you ran a convolution. Again a convolution. Now let's say you already had 3 images. Now you ran 3 again. So 3 for each image will give you 9 images, right? So you'll have 9 images. then again you ran a max pool, then again you'll do pooling. So eventually what will happen is your image size, if it was 50 cross 50, this will end up to, let's say, 7 cross 7, or let's say 1 cross 1. But its depth will increase. Its depth will increase to a very large level. And this will ultimately convert it into a dense neural network. And this is what our idea is also. Right. Let's import the first thing first. Import Keras, our best friend. Then we have NumPy, a second best friend, as env. Import matplotlib.pyplot as plt. Okay, I can remember these only as of now. Okay, so how many of you face problem in downloading the cat dog dataset? Eventually, everyone should have this problem. And I told you the solution also. If you are to download cat.dataset, then make sure that you are activating your Kaggle profile through your phone number also. Then only you will have this download button activated, right? If not, it won't work. Let's go to keras.preprocessing.image, and then we have image data generator. Then you have from keras. Okay, let's do the layer 1 and afterwards. And let's make the data generator. Data generator is, today let's make 2 data generators, not one for validation and one for but I don't have the images for both the two. Okay, let's split it accordingly. Okay, we'll do this. Okay, image data generator, what does it take? It takes multiple things. How many things do you want to give? Let's say rotation range should be what, 40. I'm sorry, I have to see this thing with shift range. How much? 0.2. Then we have height shift 0.2. Right, we can, what else do we have? Height, width, and then okay, we can do a flip also. Okay, horizontal flip equal to true. We can move this GTM a little better. Okay. Then we have zoom also, zone range. Let's do this as of now only. So our data generator is ready. Data gen is ready. You can see all the things by going here. It can tell you whatever things you have taken, it will do. I forgot to tell you one thing, that if you remember in the previous sections when we were doing MNIST, what we were doing was we were taking the whole image and then we were dividing it by 255. Why? Because we needed to normalize the image, right? Now when you are using image data generator, you can do the same with just one thing. You just say rescale. And I think we forgot this thing last session, so I'm telling you, 1./255. So now what will happen? All your images will be through your will be multiplied through divided by 255, right? Again, your data generator is activated. See, data generator, by saying it's a generator, so it will not give you all the values at once. It will give you the results in batches. And I think we discussed this last class also, where we read this, that generates batches of tensor images data with real-time augmentation. The data will be looped over in batches, right? Arguments, feature wise is boolean. You can go through all this. Next we are going to do is that we have made this generator here. Now what we can do is we can directly start with our modeling part, right? Would anyone like to help me in preparing the model? From keras.model import sequential, right? From Keras dot layers import conv2d. Today we're going to do conv2d, then maxpool 2d, then we will use flatten, then we will use dense. What else should we use? That's it, right? And from Keras dot activation, let's import activations. So what kind of activation do we need? Relu and softmax. Softmax, right? Then Keras dot losses. Maybe we'll use categorical cross entropy, right? And from Keras dot optimizer, import SGD and RMS prop. Okay, let's activate all these things. I think we are almost done. We have taken layers, we have taken activations, then we have taken losses, optimizers, nothing else, right? Let's make the model. And before we make the model, let me shift this, drag this here, and close this thing out. We get more space, right? Now let's make the model. Model is equal to sequential type of a model, right? Sequential type of model. Now let's pay a little bit attention that how do we make a model out here, right? Let me give some space and then okay. First of all, what I'll do is I will add a conv layer. I am not going to convert this image into a 1D image by doing a flattening. This time I am going to give the image as conv2D as it is. Now you remember that when we were running the convolution in practical, we had this 2D image. We were not doing it as flattening. We were not doing it row major or column major flattening, right? We took the image as it is, right? So you are going to take this image model.add convolution 2D. We're not going to do the flattening part. Now let's see that what does this conv2D takes place. Now conv2D first takes place filters. Okay, let's see what filters is. Then we have kernel size. Then we have strides. If you don't give strides are by default 1x1. Then you have padding. Then you have data format. Then you have dilation. After that, all these are like default values. They already have some values. The only two things that it expects from you is one is the filters and another one is the kernel size. Now filters is nothing but it's the number of different types of filters that you want, random filters that you want to run on your image, right? And second is the kernel size. Now when you're making this filter, what should be the size of the particular filter that you're going to run on the image, right? So you're asking this the same. You'll be telling the conv2D Keras that these are the number of filters that I will use. Let's say I use 64 filters and this should be the size. Let's see more deeper into this. See, sorry. Okay, now one more important thing, when you're using this layer as the first layer in the model, provide the keyword input shape. So you have to make sure that you're providing the input shape, right? And your input shape is equal to 28, 28, 28. 3 means that for 28, 28, 28 RGB pictures, right? And you have to make sure that your data format is equal to channel equal to last. It means that whenever you're specifying your dimension as 28 cross 28 cross 3, here 3 means that these are the number of channels. But if you are giving 3 comma 28 comma 28, make sure that you change your data format as channel first. So this used to happen a lot when there was this framework called Theano. So Theano has this had this problem, not problem, but it has its own functionality that it used to take the images in the format of sure. So I'll do this. So Theano had this own format of having the channel first. Then TensorFlow came in, it said no, I want the channel at the last. So there was this conflict a lot. So now you have to specify, because Keras used to support both TensorFlow and Theano backend. So it has this thing called data format where you can specify that you will be providing your channel first or channel last, right? But Theano ended in 2017. So, no, 2017, yes. So you don't have to worry much about data format. Data format should be channel last only. I think all the major DL frameworks are taking it in the last now. Okay, coming back to the filters. Now this filter, you are expected to enter a integer here. Now integer, it means that the dimensionality of the outer space, that is the number of the output filter in the convolution. It means, let's say if you give it numbers 32, it means there are 32 different filters, random filters that will run on the image and they will produce the convoluted image. Second is the kernel size, an integer or tuple list of integer 2 specifying the height and width of the 2D convoluted window. Can be single integer to specify the same value for all spatial dimensions. So it means, let's say if you give it this thing kernel size is equal to 3, this means that you are trying to have a 3 cross 3 filter. Or if you're giving 3 cross 4, it means you want 3 rows and 4 columns as your kernel size, right? Strides is, again, you already know, such strides can be integer or tuple, same as above. If you don't specify, by default it is 1 cross 1, right? Then you have padding. I think we talked about padding also. Padding is either valid or same, right? It is saying that same is slightly inconsistent across backends with stride is equal to 1 as described here. So you should always take it as a valid one, works better. Then you have data format. These are all like numbers that are already predefined. You don't have to look much about it. But let's start with the convolution 2D that we have to make, right? Let's say that we want 32 images of 3 cross 3, right? Next, you have to give it as a input shape. Input shape, let's say that we are going to give 150 cross 150 cross 3. We have still not decided how our shapes of the input will look like, but we have decided that we'll go with 150 cross 150 cross 3. Now once you have specified this convolution, you have to specify a activation function also, right? Either you can specify here only in this con thing, you can just go and say activation is equal to, or you can specify by again saying here model dot add, and then you can have a activation is equal to, okay, we have not gone here from, okay, so you can add an activation layer here also. I generally don't like this, I just add it here only. Activation, we love relu, we'll go with relu only. Relu is the most important thing. Okay, now does someone remember after convolution and then doing an activation, what was the next step that we used to do? No? Okay, we used to have a max pool. Max pool again, let's go. Max pool, what was max pool doing? Max pool was doing nothing, but it was bifurcating your image into parts that you specify and then picking up the maximum value out of it, right? So it's saying that your image, let's say the pool size is 2 cross 2, it means that the image will start from the kernel size of 2 cross 2, and then out of the 4 values it is going to take the one which is the maximum number, right? But let's say we want to change this. How to change this? You say pool size is equal to, let's say we take it 2 cross 2 only. Now this thing that we have written till these these 2 lines which contain 3 specific operations, this thing is called as the chunk. Single chunk of convolution. These 3 steps. Which one is the one? One is conv, then you have activation, and then you have pooling. These 3 things together are called as the chunk of. Now what you can do is you can just copy paste these things and then you can have more chunks. But this time you have to make sure that you're not using this input size, because input size should always be inside your first thing only. I'll increase this number to 64 here, or let's keep it 32 only. Again, I will copy this thing let's make 3 chunks because our data is not that much complex. Let's have 32, 34, 64, and then come here, and then you have model.compile, right? Compile me, you have loss is equal to categorical cross entropy. Let's bind it in double quotes. Then you have optimizers. Let's use SGD only. This is the one that converges the fastest. Then you have matrix. Let's use accuracy, right? And then we'll do model.fit. But as of now, we don't have any input outputs. Let's just make the model sit here only, right? Nothing much to do. So what we did actually here is we did nothing much. We just made 3 convolution filters. One is this 32. When we started this off, 32, we said 32 numbers of different so imagine this one image will now become 32 images, but the size will drop due to max pooling, right? Again, these 32 images will now become into 32, but their size will decrease. Again, the height width will decrease. Now these 62 will become almost like what will they become? They'll become 64, so they'll become more, and their height width will again decrease a lot. One thing that I forgot to tell you is that this is not the end, right? Our end will be somewhere when the output will be only 2 units, right? This is not the output, right? We have to do a flatten here. Remember? Because ultimately, see, our answer will be in 2 words, right? Either 0 or 1 in 2 letters, right? So the output layer will only have 2 neurons, correct? Model.add once is flattering. Flattening. We have done the flattening, then we might use a dense layer. Dense layer, let's say we take 1024, then let's add activation. Let me add it here only in this thing. Activation is equal to relu. Then let's decrease this by, let's say 512. Again have activation of relu, and then in the end let's have the final well will have how many? Only 2, dense and 2, and this time the activation will be softmax, right? So this will almost become like this, if you remember. So our model should almost look like this. Just a second. This. Does this look like the same? So first convolution, then pooling, then second convolution, then pooling, then imagine we have a third convolution also, then we have a fully connected dense layer, and then we are reducing the number of dense layers from 1024, then 5112, and then immediately 2. So this example has more, but this is somewhat like what we have an inspiration code, right? So I think we already have this data generator here. Let's add just one data generator. Now what we have to do is that we have to make a train generator. Train gen is equal to data gen dot flow from directory, right? Flow from directory, where is our data? Our data is just behind this. Then we have cat dogcat. Yes, dogcat small. We have more generator small. You all know what should be the format of this folder. The format of this folder should bear, let me show you. these questions are coming to your mind, that how did I come to this number called 32, right? First of all, and then how did I take this kernel as 3 cross 3, right? So one is the experience, that slowly when you will be practicing more and more and more, what will happen is, now by seeing the image, by seeing your data, what is the dimension of your data, then seeing the complexity of the image, you will come to this number, how these numbers are coming. Secondly, let's say that, see, I am not a researcher, so what I generally do is I read papers. Now if you read the paper of VGG, let's say if you read the one of the best models that are available for VGG, you will see that these models, my code is totally inspired from it only. Just a second. VGG, here it is. So if you go here and then you see, this is one of the VGG was written by Oxford people, where they made this. So if you see, this is how they have made the VGG model. Sequential modeling, then adding convolution 6433, and believe me, they have done more than thousands of iteration, and then they have come to these numbers, right? So I am doing nothing, I am just also following these people, and slowly, see, not only following these people, but when you will start your when you will start your modeling thing, when you will slowly start learning about these things, when you will be exploring, then you'll understand how these numbers vary. So let's say why I am taking 32 or 64. First of all, 32 and 64, why? Because there should be that the number can be any number, but we generally prefer them to be in the order of 2 to the power. Because if you will see the maths behind this thing, if you see the maths behind the convolution, you'll get to know that, okay, all your calculations are done with the numbers in 2 to the power 4, 2 to the power n, whatever where n can be stand from 1 to whatever the number is. And second thing is that to avoid any kind of a miscalculation, because sometimes, let's say, your measurements are not working finely, it might be padded with zeros or ones, like we generally saw in the padding, right? The padding can be a valid padding, or it can be a smooth padding. So depending, and not having not having much wrong data inside our model, we generally try to have this thing in 2 to the power, right? Second is, these are the numbers of different types of numbers that we are having. Let's say your image is a normal image with not much information, and let's say you have 1,000 filters right here. First of all, your RAM will exhaust at a very high speed. Second, that you won't be able to extract much information. So let's take an example of let's say that there is some task that needs to be done by some people, right? And the task is only for 3 people. Now if you deploy 15 people out of there, the total contribution will be equal to what you have given, but individual contribution will be very less. So that will also happen if you increase the number, let's say the 64 to 1500 something, then the total contribution will still be the same, but the individual contribution will get to really low number, right? You're getting what I'm trying to say here, things.
Yes,
Now
yes.
second, you might also ask that I might reduce this number also. Let's say instead of 64, I might have taken 32 only. Now if you would have taken 32, those 32, now imagine the same situation. The people, there's a job that needs to be done by 64 people. Now if you're employing only 32, now the total contribution will now also be affected, right? The total answer that you want out of your job will also be not be equal to what you desired, right? So there should be a balance in this number, and believe me, deep learning models are not like that you sit one day, just write the code and then you present and the answer is there. It's a process of reiteration. It's a process like somewhat like this. You start, it's like a circle, right? You have your deep learning model here, and then you do multiple iterations. You have a deep learning model here, and then you do the iterations again and again. You're changing your parameters. You have your parameters p here, and then ultimately you have a boolean here. Do you say that your accuracy, your error rate decreased or not? If yes, then you go out. If no, then you again go to the circle, change your parameter, again go up, right? Are you getting what I'm trying to say? Make sense? You will again go up, go to the DL paper, DL code, change your code. Now again you'll check your error. If it is correct, you will go out. Otherwise, again go in. Change parameters, again go. So it's an iterative process, and iterations depend on the data, its quality, and the most important thing is differentiation. See, we are doing a very simple problem here, cat and dog, and it's quite easy to differentiate between these things, right? That you create a model that will give differentiate between you for like cats and dogs, right? But if complex are there, then so this VGG model is one of the most complex models because it is catering 1,000 categories, 1,000 general categories, ranging from little birds till like aeroplanes, bikes, motorcycles, human, Homo sapiens, and apple, fruit, everything. So almost like 1,000 categories that are covering, and this model is like one of the best models, one of the best I'm saying, because it's a very lightweight model and it is giving a very greater accuracy. Now there are models where you have 100 layers of models, those are also giving you accuracy, but those are not optimized models. Those are like very heavy models like ResNet 101. So we have this VGG, and this is best in its nature. Okay, so jumping back to the thing, so we have data generator. We have to create a data generator out of data gen. We have given the folder. You all know how the folder looks like, right? LDIR is equal to, if I show you what is inside data generator small, then this is nothing but the two folders, category wise folders, right? These are
One
category wise
question.
folders. Okay, so let's move back here again. So we have our data generator here already. We will say that please go to this directory data generator small and then flow these images from this directory, right? I'm also telling it that you should have a target size of 150. So whatever the size of the image is, resize that image. Again, listen to me. I'm saying resize the image. Do not crop the image. This is not cropping, right? So if your image was 1056 cross something, this is not getting cropped. This is resizing the image, right? So you are saying that you want to convert your image into this, then you have to give the batch size, at how many images that you want to read, right? Let's say I want to read 32 images per batch. Now you remember we have 400 images for all the classes, for all the two classes. Now I am saying 32 batch size. 32 batch size means that if I divide 400 with 32, it will give me around 12, 12.5, or let's say 13. So this is always sealing. If you remember, this is called sealing, np.sealed. So this will always be a 13 buckets we will have. So our epoch will show a count from 0 to 13, right? Makes sense to everyone? Batch size 32, and then what do we have? We have data generator, then we have color mode, it's already RGB, then we have classes is equal to none. We need to keep it none. Then class mode is categorical. Yes, we wanted categorical only. We have batch size of 32, it's by default. Shuffle equal to true. Yes, seed equal to none. We don't want seeding. We save directory. No, we don't want to save. Nothing. We don't want to save. We want to just start the thing. So it says that it found 401 images belonging to two classes, and that was correct. We had only two classes. Right. After we have got our train gen ready, we should use the model.fit, right? But no, here we will not. Okay, sorry. Is it now visible? Cool. So fit will not work here. We will use fit transform. Model.fit generator. Sorry, not transform, generator. Model.fit generator, you have to give it what? A train gen that you have just made. Next, you have a step per epoch. Step per epoch is none by default, but this is what you think, right? Steps per epoch is what? That how many buckets will come here. So you get the idea, right? What was the number that we just calculated? That was 13. I'll tell you again how it came 13. So you have 401 images in total, right? And you are saying that you will have a batch size of 32. Batch size of 32 means that in each bucket you will have 32 images. Then how many buckets will you have? 12.53. Now bucket can be an integer only. So what you will do is you will do np.ceiling. It means you want the upper bound. Upper bound will be what? 13. So you will have 13 things. Or what you can do is, that is the most brilliant thing that all you always do is +1. That gives you the idea, right? So what we are going to do is we can write here that steps per epoch will be, so one epoch is what? When all your images are gone from the model forward and backward once. That is one epoch. Now you have 400 images. You are only taking 32 once at a time. So your model will be taking 13 times each bucket of 32 images, and then it will cover 400. So your steps per epoch will be what? 32. Make sense to everyone?
Yes, sir.
Yep. Then you have epochs. Let's say 10 epochs only right now. I don't have much RAM in this, but okay. And then you can say verbose equal to 1. Verbose equal to 1 means that you want the output to be printed. Yes, we want. You can have 0 or 1 dependingly. And they have 2 also, if I remember. Yes, verbose is equal to 0, 1, 2. 0 is like totally silent. You don't want anything. 1 is with the progress bar, and 2 is with the one line one line per epoch. Right. Okay. Then you have these things called where is this? Class callbacks. Now this callback is a very good thing. I will let you know. Today only we'll cover this callback thing also, and we'll cover what is TensorBoard. Right? How, when you are running a very large model, how do you see the losses and the accuracy of this? Right. Similarly, you can have validation data. If you have validation data, you give your validation data where it is. Right. Validation steps. How many steps do you want? And then you can further give this thing. We don't have much. We will say we will remove this thing. We will run this again, and again. And our model is started, and my CPU has started heating up. Okay, let me stop it here. Sorry. I forgot to do one thing here, that you have to take this thing in some output history. Now we will start this. Sorry. See, I told you this number is going to be 13, right? Is everybody getting the idea? So we are saying that we want 10 epochs. That is a different story. But in each epoch, how many times it is going to run? 13 times. 13 times forward, backward, 13 times. And each forward, backward is taking how many images? 32 images. Now you can see your model is giving 54% accuracy. Losses are decreasing, 0.69. Oh, 70 increased. 69 decreasing again. Okay, this was a very bad line. The accuracy decreased. Okay, the model is recovering slowly. Oh yes, increasing. Just 2 more steps and our modeling will be done. This is how we do. Now let me check one thing, because I think I did something. Because this is not what the accuracy I was expecting. The accuracy should be like, okay, so we have a data set also small one. If I give it the big one, let's try it. Then it should work better. Okay, let me run this again. Let me restart the kernel only. Epochs are also less, so you might try to increase the epochs also. And I might need to do one more thing. I might need to increase the batch size. Now, can any one of you tell me how is the batch size affecting the model? One is that, okay, it is using the RAM, right? Because 128 images are now going inside the model. But what else it is doing?
$120 resumes
My
divided
batch
by
size right now, I have changed my batch size from 32 to 128. What will this change? Okay, this is going to take a lot of time.
The number of to and fro that will change, right? In one cycle, one
That is
epoch.
one thing. Yeah, that is one thing that I totally understand, that you say that this will change, right? But what else will also change?
More data to the model.
Correct. More data to the model, but not totally. See, the images are still 400 only. But your answer is somewhat correct. The images to the model will increase, but how? Because the total number of images are still 400. Then how are the number of images increasing?
Feeding. We are feeding the images to the.
Correct. So let's say I give you this example. Let's say that there are two animals that are not known to you, right? I am giving you the images that this one is animal A and this one is animal B, right? Now, if I show you only one image at a time and then I ask you that tell me who this thing is. Or another case is when I'm giving you 100 images and then I'm saying 50 are this, 50 are this. And then you see all those, okay, 50 animal A, 50 animal B. And then in which state you will be able to give, when I give you next image, in which state you will be you can give me better answer. Did you get my question? What I'm trying to say? Okay, I'll come again. There are two scenarios. There are two unknown animals, right? And now you are the person and I'm asking you that you have to predict which animal it is, right? But before predicting, I will tell you this, that which animal is which animal is which, by showing you a different picture to you. I have two boxes, right? First box may I open, and one case is that I only show you one image of each animal. One image of animal A and one image of animal B. And then I ask you that predict this third image.
Correct.
Right. And another case scenario is where I show you 100 images first. 50 of animal A and 50 of animal B. And then I give you some image to tell me that which animal it is. Which case is better? Which case is better to you?
Yeah, later one.
The later one, right? Where I show you more examples. This is also what is happening with the model also. So if you try to understand that, okay, let's say if you are taking a batch size of 32 and a batch size of 128. Now, when the images are going inside, what is actually happening? These are convoluted, then sent to dense, then after dense they are going to reducing their dense, and ultimately they are giving some probability, right? Now based on the probabilities, the model is saying that this is your error. and then based on their error, they are again coming back and then they are doing some differentiation. Correct? Now imagine that you are showing your image only, let's say 8 images. Now the model is trying to change the model is trying to change the deviations, your gradients, by seeing only 8 images. And let's say if only cat's images are shown to you, then the model can get biased, right? And let's say now in the other case, we are giving more images. Now by seeing more images, it tries to be more generic in nature, right? Make sense? How things are differentiated? How is this thing like only giving 8 images and then across giving 120 images, and then based on those images, is someone, if it is bringing some change in itself, how it is going to change, right?
Yeah, basically accuracy is increased.
Yeah, accuracy will increase. Correct. One thing is that accuracy will increase, but I am just worried about one thing, that okay, our accuracy is low. I understand this thing, that is this that should be low because we have like very less data. Okay, so I have some questions now. It says it's always better to have a big batch size. Yes, to make your model generic, I think your model should have a good batch size. But again, batch size is again not in your hand, because let's say you're having a less computational heavy machine, then your model won't take this much of images in one go, right? So you have to decide very wisely how much images can you handle in it, right? So it's a trade-off. You cannot even have a very less number, and then you cannot have a very large number also. Until that, let me review the model again. Cross-entropy, SGD. SGD is one of the fastest one uh, to converge. But let's say if we use RMS prop with no delta, let's see how it gives a number. Yeah.
Yeah, image is SD or HD image. Does play any role? Because SD image have more dense pixels.
Definitely. HD pictures are like more wider, sharpen. But again, this is a problem also and a good thing also. Let's say you have a HD image, it will have more information. I agree. But more information will come with a more computational heavy resource, right? So now HD image, you have to like resize it to a normal level, right? So HD image will make no sense. But let's say you're not resizing, let's say you're keeping it as constant as it is, then you have to deal with the RAM resources. How easily your RAM is going to get exhausted. So you have to deal with that also. Let's say we are done. No, I don't think SGD is the best converger. It is converging best for us. SGD will converge best, but I want to show you one more thing here is that we have two classes right now, right? We could have done one more thing. We could have asked it here that we have, no, not here. Sorry. We could have come here and say that this is only one. And rather than saying that this is cross entropy, we could have said Keras dot losses dot binary cross entropy, right? How I'm showing you that what is the difference between categorical and binomial. So what I'm saying is why I took one only, because now my answer will be in 0 and 1. And why 0 and 1? Because if it's not a cat, it is a dog actually, right? So it's actually, so how I've converted two categorical problem into a binary problem. Binary problem is what? 0 or 1, right? Let's say 1 is dog, then 0 will eventually become not dog, and not dog in our case is cat. And this is one thing that you should always understand. Let's say that if your model is trying to predict three things, one is cat, dog, and elephant, let's say, and let's say you give a image of giraffe here, right? Tell me what is going to happen when you're trying to predict this thing. You have trained your model on cat, dog, and elephant, and now you're giving it an image of giraffe. What will it predict? 0, 0, 0. Okay, one answer is 0, 0, 0. But it will say 0 for each probability, right? Next answer, anybody else?
It might give some probability, some similarity with those animals.
Okay,
Maybe with cat will be less, dog will be somewhat means in mid, and elephant it is probably less.
totally correct. Totally correct. See, this will, so one thing that you should always remember is that the sum of the probability for the three classes will be equal to 1. You guys
One,
forgot.
yes.
At the softmax, we always use a softmax in the last layer. And what is the responsibility of softmax? That it will give you the how many probabilities? It will give you the probabilities that much classes that you have. So if you have three classes, it will give you three probabilities. And the sum of all the probabilities will be equal to 1. So 0, 0, 0 might, I mean, it will not be the answer. The answer will be that the model will say that, see, I know, I know that the answer is not right, but because I'm not trained on this, and the elephant is not matching, it's not matching even to your dog, not cat. But softmax, what it will try to do, even if it is giving very less accuracy for each, it will, based on the percentile, it will give you the probability which will sum up to 1. So Ankit was saying very correct that it might not give high probability for cat and dog, but it might give some probability for elephant and dog also, right? And it might not cross 60 or above for each of any one of the category. So it might be like 30, 20 for cat, 30 for dog, and 30 for elephant. I mean the sum will be 1. It will try to do somewhat like this. Making sense?
Yes.
So always remember, your model will always predict from only what you are trying to tell it, right? I will like to start with callbacks, because I have this sheet on 6th Jan where we did this history thing out here. History thing, we did all this plotting and all. So I think we should go with callbacks. That what are callbacks? Okay, now callbacks is a very important thing, and it's a very thing in. Oh, sorry. Just give me a second. I'll be back. Just give me a minute. Just give me a minute. I'll be back. Sorry, I'm back. Okay, so we were talking about these callbacks, right? What are callbacks and how do they help? Okay, so a callback is actually a function that you can execute after every epoch is run. So let's say that your line is somewhat here, epoch here, and then you come here. Your accuracy, final accuracy is printed, your validation accuracy is printed, and then whatever you want to do, you can do at this stage is called a callback. Again, this will be executed when your second epoch is completed with all the 4 batches. Then again at the third end after this, and similarly. So after each iteration of an epoch, if you want to run something, you get this thing inside your inside your callbacks. Now how do you get callbacks? Very easy. You just say from keras.callbacks import callback. See, callbacks is nothing but callback is that, let's say that after every epoch, once a epoch is run, and if you want to perform some operation after every epoch, you can call that function inside a callback. That's simple. So there are multiple things that you want to do after every epoch. Let's say you want to store the results, or let's say you're writing your own custom laws or let's say you are writing your own custom let's say optimizer, right? Or let's say you are decreasing your learning rate based on some particular parameters. So then you can write. I can show you. I wrote this code somewhat long time ago, and this contains a very good callback thing. Let me show you. So if I show you here, callbacks. Here I'm using model checkpoint and learning rate scheduler, right? So I'm using two things. One is called tensor, one is called model checkpointing, another one is called learning rate scheduler. Now what this model checkpointing is doing, this model checkpointing is saving the weights after every epoch. So I think someone from you just asked this question, that will it take the last step accuracy and loss? Let's say the last step accuracy is very large and you want the second last model. So what you can do is you can take the weight of the second last step epoch, right? And then you have the
Yeah.
learning rate scheduler. So the question was that, let's say that the accuracy is not actually in the last step, is not good in the last step. It is good in the second last step. So what you can do is you can take the second last step ka weight, right? So model checkpointing will save each and every weight after each epoch. Second thing is what? That is learning rate scheduler. Now sometimes you want to decrease or increase your learning rate based on the prediction accuracy, or let's say I am using this based on the V monitor that I'm using. I can show you that also. So you have to write your own custom function. So here, see, I have written my step decay function. What I'm doing here is that I am decreasing the learning rate based on the number of epochs it has done, right? So what I'm doing is, if the epoch has dropped to 3, so let's say after every 3 epochs, I'm trying to drop my learning rate to 0.5, right? So for what generally what I think the callback that you're confusing is with the web one, where we use it after a async process, or you use it after a readout of a thing where you want to call back your afterward thing. That is a somewhat different thing that we are turning from here. So if you see the callback documentation, it says the apps. This is a base class. How do I tell you? Model dot compile, and if you say fit and then you say callback, and if I show you callback, here it is. It's a list of keras.callback.callback instances, list of callback to be applied during training. That is it, simple thing. So what it is it that after every epoch, if you want to run any kind of a function, any kind of a method, then you can specify them here in the callbacks, then they will be executed and they will be recorded in the tf.event files. Again, after the second epoch is completed, you run the callback. After third, you run the callback. After fourth, you run the callback function. So we were here at this thing that, let's say that you define your own custom step decay function. After you have done with the step decay, how do you call it? You make it your loss history, and when you are doing a dot fit, you call your callback here, right? So we'll do the same thing out here. What we'll do, we have this thing called tensor board. So if you see, I have imported this thing called, this one is not needed. From keras.callbacks import tensor board. So what I've taken is tensor board is, I'll show you what tensor board is, but let's first implement it at what tensor board is. Before you're doing your training, you have to do a tensor board is equal to tensor board. If it is in capital, it's a class. Class where you have to instantiate. You have, let's say, log dir is equal to let's say here only, or let's say that you want to make it as a logs. Okay, so what it will do, it will create a folder called logs in my current directory, and then it will store all the information there, right? What it will do, it will store all the information there only. And let's say I don't want to go in the logs folder, I just want to stay in my dot folder only. Stay wherever my Jupyter notebook is, just create the file there only, right? But you can specify wherever you want to go. Now once you have done this, this will start this thing, TensorBoard. And then while you are in your fit generator, you will call the callbacks. Let it complete callbacks, and then it will be a list. List me, you give your TB, right? And let me increase this to 15 for now, right? And let's start the model.fit again. Now while we are doing this thing, what will happen is, let me show you. If you go in the files, you see here there is this thing that has started building up, tf.event files. After this first epoch, you will see a new file here, last modified. Okay, now you will see it up here after first epoch. Okay, yes, you can see here. If I do a last modified above, okay, it's not coming. Then you have to go down, and let me show you. See if you can read this thing called here on the downside. I'm just marking it with the blue marker. This is called events.out.tf event file. So what it is generating is, the TensorFlow is generating its event file, and they are stored here. Now how can you open a TensorBoard? Very simple. Open up your console. You go there in the console. Click on the console. Okay, this is Windows. This will take a little bit time. Enter, and you have to just say TensorBoard. TensorBoard is by default installed when you are installing TensorFlow also. So TensorBoard TensorBoard -- log dir is equal to, or I can show you the help first. Sorry, board -help. Okay, this is not good. Should start this thing. Okay. Okay, let me run it in a simple environment. Just a second. This is your IntelliPad working directory. We are in notebook 3. We are opening the CMD. Don't worry, I'm going to show you. Just a second. Let me open it up. So see what I ran, I just simply said TensorBoard, and this will start the TensorBoard inside the directory, right? Now once, okay, I did a mess. I should have specified this thing, but okay. First thing first, I should show you the help -help, that what are the different parameters that you can give. There is one parameter that is called log dir that you have to definitely give, that where your logs are kept, right? Where your logs are kept inside which directory. Okay, this is taking a small time. Okay, so now they have changed it to helpful. It's not help. Okay, so these are the different flags that you can give. You can give a tag if you're running multiple. You can give port number, which port do you want to run. But the most important one is this hyphen loud dir. This one is the one that is the most important that you have to give. There are multiple things that you can do with TensorBoard, but the most important is when you open TensorBoard and where you are. So I'm saying dot means wherever you are present, the log files are present there only. Let's go to our browser again, and in the browser, let's open up our localhost 6006. That is the by default port that we have. Takes time to run this thing. Let me check. Okay, so it runs on this thing. Change the... So here what you can see is the beautiful TensorBoard. It's loading. Does multiple tabs, and let's if we see our model is running on the 11th epoch. So you will have all the information till 10th epoch in this thing. So you can see the dashboard is here, and these are the loss and the accuracy function. These are the same numbers that you have here. So you have something that is greater than 7.1.0. And if we go back to our model and if we see what is the accuracy on the first epoch, that is 50.3. Sorry, this is the loss 71.6. Sorry, it's correct. So it's showing you the accuracy on the top and losses at the below. So your loss was greater than 7.10. If you go on the mouse, if you put it somewhere, it will show you each and everything, right? You can smoothen it up more to see the exact accuracy number. If you're running larger numbers and you want to smoothen it up, then you can smoothen it up with here, right? And this is for loss. Whatever different kind of if you would have validation accuracy or validation lot, they would have also been plotted here. These are the two things that you can definitely see here. So you don't have to actually view this this thing here. So what you can do is that you can quickly come up here and you can say, okay, my step number 6 is the best. This is performing the best. I will take its weight, right? Same here also for the 6th step, you had the lowest loss and the highest accuracy. So you'll say, I'll take this one, right? Now the most important thing is visualizing your model. So if you click on this graph button, you will see your model here, how it looks like. This is how your model is actually. So if you can zoom in, you can zoom in and see how these things are. First you had this convolution one, right? Then you had a max pooling, then con, then max pooling, then con, then max pooling. Then you had a flattened layer, then you had a dense layer, then again a dense layer, and then you had a matrix to identify what kind of a matrix what kind of accuracy it is, and then you had the loss here. If you click on this loss here, you will be taken to the loss section. On the right, you can see that this is giving you all the things out here. You can also shift your model here, and then you can see this is how your zoomed in variable is. Sorry. So if you click on each thing, then you can have this. Let's say I click on this dense layer, then you have this thing on dense sub node 13th node. This is the 13th node. The input is coming from dense 4. That is absolutely right, because dense 4 is there, and then you have dense 5. And then the output is going in dense 6 for the matrix multiplication with 512 variables. And that is absolutely right, because in the first we had 1024, then we had 512. And then the output will be in the form of 7 tensors. Absolutely correct. If you go this thing and if you just do a model.history, it will model.summary, it will be the same, right? These dimensions are the same that you see here. Then you have control dependencies. If you want to have more information on the graph, then you should definitely show this to client. These are like showing here. You can go anytime, you can go there. So why there are like two? Actually, there is only one, but we are showing this as two because it's my mistake. I did this one thing. What I did was I actually ran this twice. I should have restarted the kernel and then I have done. It would have been only one, but I'm running. I am stupid. I should have not done this. That's why it's showing two. Otherwise, it would have been only a one. And here you have all the things. You can click on each and every sub node to see what is happening inside, in and out. Right? It has multiple things. You can even see images inside it. So right now we are not given, but if you would have given, you can see your things out there also. I'm so sorry. I have to go back. Graph. You have multiple things in here. You can download this graph also by clicking on this fit to screen, and then you could have download this also. Session, you can see multiple devices also. Let's say I have only one device. You could have multiple devices, and then also you could have taken trace inputs. So you want to see where your inputs are going till now. Let's say if I click on this, it will show me how is my input working for this particular section, right? Choose legends, whatever you want to have, right? It's a very useful thing. You will come to know more about this when you're training, very large layered networks, when you're training good level of networks there. In our relative number means what is the difference between the previous and the past one. So it's like a step function that you're doing. Then you have the step is the exact one that the recording for each epoch, and relative is that you're trying to get the number from the previous one, how it is changing from the previous one. You have this wall one also. Wall is for time, so according to time. So again, I'm saying these are for like very big models that are running for like 5 days, 6 days, so you can convert them into time also, wall time. Then you have like 950 with accuracy was here, 955 with accuracy was here, then right, makes sense. But the only thing extra that you have to do, two things that extra that you have to do to bring tensor board was that first of all that you have to tell the model that model please after every epoch you have to save this things for me inside this file call through this callbacks ko you have given a list me you have given tv is actually what, it's an instance of tensor board. And tensor board, how did you declare it? You declared it from keras.callbacks.tensorboard. Now once you are done with this tensor board, how did you open the tensor board? Tensor board you opened in the command prompt, you went to the folder where you are running this thing, and then you just write tensor board -logdir. Let me write the command here also so that you get the idea. Tensor board tensor board -logdir, and then wherever your dir is actually, so r was dot wherever it was. If you would have been in logs, then you would have given logs, and then you would have changed it here also. Right, and then you start. By default the port number is 6006. This is the number where you use, this is the port number. If it is used, it will increment by 7, it will increment by 1, so it will become 6007. You can specify it also while you're starting a tensor board by giving the parameter called hyphen port, right? These are all the things that we have today. So today we covered the most important thing was convolution. We learned about how convolution, we have to implement convolution with augmentation, right? Then we learned that last week that we saw this image. Today we implemented this image with the augmentation, and then we did this tensor board also. So I was saying that if you want to run your tensor board on some different port number, then you can give the port number when you are giving this command on the command prompt. So you can specify here like hyphen port is equal to 700, let's say 9, 6009, or let's say 7009. So you can give it here. Tensor board has to do nothing with Jupyter Notebook. Even if you are running it on a blank .py file, or if you're running it PyCharm, you're running it Spider, it doesn't make much difference. But the only thing that I always push pressurize is that you should do data science in Jupyter Notebook because the answer is available to you instantly. Some people, some of my friends are like very against it. They use Spider. So it's a personal choice. You might use Spider, you might use what, but you can run Jupyter TensorBoard wherever you want. TensorBoard in itself is a very separate entity. So if you remember, we ran it through a command prompt. I ran something in the command prompt and then it gave me this thing here, right? So if I show you the command prompt, see, this is the command prompt. I ran this whole command here, this thing till here, right? TensorBoard -logdir, and then it gave me that TensorBoard 1.8.0 is running at this address at port 6006. Press Ctrl C to quit. I just copied this thing from here, went back to my Chrome, and I just copy pasted this and I run this. So this has to do nothing with your ID, whichever you want to use.
So, suppose you are a computer vision engineer and a client has approached you with a problem statement in which you have to detect the faces from a set of images that they will be providing, and you have taken up this project, and these are the following steps that you have to follow while building up this project. So, these are the images that they have provided to you. These are some of the images that have taken from their dataset, and here we'll be working on Python with OpenCV. In this project, we will be using the Haar Cascade classifier for detecting the faces from multiple images. So, firstly, you have to perform the downloading part for the Haar Cascade system. So, here I have written download Haar Cascade frontal face default.xml and this raw GitHub code. These are the raw datas for the Haar Cascade. You have to just simply save as, and you can save it as desktop, and you have the Haar Cascade classifier. So now next we will be just importing the CV2 and glob. So now we will be practicing it in the Jupyter Notebook. So firstly, you have to import the CV2 library and glob. So I want to tell you that glob is the function which returns us the array of those file name which we will write in the next line. Like we just have to perform face detection on those images which have .jpg extension. So for that I will be writing gimage equals to glob. So here I am calling the object glob and with the function glob, and here inside the function I will be writing the star.jpg. So it will take up all the images that have extension .jpg. So after that we will detect after getting the glob images. Now we will create cascade classifier so that we can, so as it helps us in getting the face detection. It contains all the features of the images like nose, ears, face, object. These are some of the features of the image. So here we will be writing detect equals to cv2.cascade classifier. Then inside the braces we will be writing which classifier. We have downloaded the Haar Cascade frontal face default classifier, so we will be mentioning the same name, Haar Cascade. Okay, Haar Cascade frontal face default.xml. So now after creating the Haar Cascade frontal face default XML file, then what we will do, we will now traverse the glob images so that we can detect the faces. So for traversing, we will be creating a for loop for traverse, or you can also write timage for traversing the image, timage in gimage, the glob image. Okay. So now it will take one image at a time. Now in the for loop, we will read the image, a particular image. So for just reading the image, we will write like I have taken image equals to cv2 dot I am read. And what is this reading? The T image. Okay, so after reading the particular image from the G image, now we will convert the images. These are the colored images. The image that it has read, it is the colored images. So in this phase detection, we will first have to convert the colored image into the grayscale image. So it is easier for the classifier to handle the image and detect the faces from it. So for converting the image from converting the colored image to grayscale image, we will write gray image. I have written this gray image equals to cv2 dot cvt color color, and in the braces it will have this image that you have to convert it into grayscale. This image comma we will write cv2 dot color and underscore bgr to gray. Okay, so after converting it into grayscale, now we will detect the faces from the images. So for detecting the faces, I will be writing the face equals to detect. I am calling this object here and with the function detect multi-scale, and it has 3 parameters. So the first one is in which image you want to detect the face. So we will be writing this gray image here, and the next parameter is the scale factor. So we have to see the value of the scale factor, as the scale factor is that value which decreases the volume of the whole grayscale image by 5% until the face is detected. So it basically what does, it decreases the value of the image so that it can find the face from the image. So I am writing 1.25. The smaller the value is, the greater will be the accuracy. So I am writing 1.25, and the next parameter is the minimum neighbor. So we don't have to bother this value. Now after that, after detecting the face, now we will be describing the rectangle shape for the face. So for that, create a for loop for. Now in this braces, we will be writing all the dimensions for the rectangle like x, y, w, h, length, breadth, height and width. Okay, so after the parameter, now in face, we are actually we have detected the face, but now we have to define that face with a rectangle shape. So for that, we will be using the dot rectangle function. So here I am writing cv2 dot rectangle. Okay, rectangle. Now in this we have 4 parameters. The first one is the image that you have to detect the face image, this image that we have read it here. Okay, the second parameter is the RGB value. RGB value means the colored value. So here I am writing the x, y, and then the other parameters for the rectangle. We are basically defining the parameters of the rectangle, how it will look on the image. So we will be writing x plus w, y plus h. Okay, so after defining the parameters of the rectangle, now we will be look at the color of the rectangle. So here I am just taking the green color. So this is the code for green color. Okay, 0,255,0. Okay, so now after that the last parameter is the thickness of the rectangle. So I am giving 2. So now after defining the rectangle, now we will just show the image. So for displaying the image, cv2 dot imshow, in the parenthesis we will be writing detect any message you can write, like detect images, okay, and comma which image, this image, so image. Okay, so after displaying the images, now we will be defining the wait key function. What does wait key does is we will define some intervals between the images. It's just a time period that what will be the intervals between the images. So cv2 dot wait key, and how many I am taking 200 milliseconds, sorry 2000 milliseconds, and we will be writing cv2 dot destroy all windows. So destroy all windows will closes all the windows based on the wait for key parameter. So here I am writing the 2000 milliseconds, so it will destroy it for that. So here, okay, so I am running this code. So here you can see that all the faces have been detected. Okay, so I hope you have liked this session.
Now, if you guys want to become a certified artificial intelligence professional, we recommend that you read through the description that's below. We at IntelliPart provide all courses of artificial intelligence covering up all major concepts. We hope this video has brought you enough knowledge on the field of artificial intelligence. If you have any comments, please don't hesitate to put your comments down in the section. We'll reach out to you immediately. Thank you guys for watching the video. Hope to see you again soon.